Okay. Now we have time.
Yes.
Right, agree.
Hi.
Hey, good to see you. Let me see, Peter is also here. Hi, Peter.
Hi. Hi.
Arun,
Yes.
are we already beaming live on YouTube, or this will start at 1:30?
It will start at 1:30, sir.
Okay.
YouTube live streaming will start exactly at 1:30.
Okay. So then we can chat among ourselves.
Live streaming started, sir. So live streaming is ready now.
Oh, it's ready? Okay.
Hello, Sudhir.
Yeah, hi, Bimalda.
Yeah, good. How are you?
I'm good. Thank you for being here. I know you joined long ago, but you stepped out.
Yeah, I was here and there. This is
Good.
I was here, but here and there. And now it's 1:30, so I'm there. Okay,
Yes.
you can start.
Thank you. So, Arun, we are waiting for your principal. Is he going to join?
Yes, sir. Director sir has joined. I just want to confirm.
And
Professor joined.
Kokre is there.
Professor Kokre, yes. Professor Kokre is there.
Yeah, Mr. Fawade. Prakash. Yeah, good to see you.
Hi.
Hi, Sartaj.
Yeah.
Hi, Pigme. This is Arun.
Yeah. Yeah, Tigway is muted, so I think Arun was saying hi to you. Let's see, I guess we can, my watch, we have still 1 minute to 1:30.
Good morning,
Yes,
everybody. I'm Prakash Vivare from Indore.
Good morning, sir.
Sir, just 1 second. I just call Professor Joshi and then we continue.
Good afternoon. Professor Ghorpade, good afternoon.
Good afternoon, Professor.
Good afternoon, sir. Good afternoon, sir. Welcome, sir. Hi, Sartaj. Sartaj, hello.
Hello. Yeah, can you hear me now?
Yeah.
Okay, great. Yeah.
So can we start, sir?
Yeah.
Because people are joining on YouTube link also.
Yeah. So I guess I'll request participants to mute their audio. Arun will start the proceeding.
Okay. Greetings and welcome to everyone here. And thank you for joining us at the International Workshop on Cryptography and Coding Theory 2021, which is being conducted in virtual mode. I am Arun Kumar Patil and one of the organizers of this workshop. A special welcome to chief guests for this inaugural function, Professor Bimal Roy, who is the head of R.C. Bose Center of Cryptology and Security, Director Professor Y.B. Joshi. He is the director of HGS Institute of Engineering and Technology, Nanded, who is the host institute, and the coordinator of the Center of Excellence in Signal and Image Processing, Professor Manish Kokre. A warm welcome to our eminent speakers and participants who have joined us from all over the world. It is my pleasure to welcome you all to this holy city, Nanded. Virtually, I am welcoming at Nanded. Friends, Nanded is a very famous city for Sikh Gurudwara, where the 10th Guru of the Sikhs breathed his last here after devoting his entire life to the service of mankind. And on the map of India, Nanded is a very nice location. If you draw a vertical line from the capital city of India, Delhi, and horizontal line from the Mumbai, which is, we can say, financial capital of India, the intersection is Nanded on the map of India. So very easy to find out Nanded in the map. We are indeed honored to have you with us and also looking forward to seeing you all in the reality mode in this beautiful city Nanded, hopefully in future occasion. We have about 390 participants across the world. At the moment, 398. The number has reached 398. And they're from all over the world, from Brazil, Denmark, France, Germany, Indonesia, Italy, Malaysia, Mexico, Morocco, Netherlands, Norway, Spain, Switzerland, Turkey, USA, New Zealand, and of course from India. And they are gathered here today making our workshop truly international one. I wish everyone a fruitful virtual stay with us for the next 5 days, friends. And now I request Professor Sudhir Ghorpade to take over the program further. Thank you once again to all of you. And now I request Professor Ghorpade. Professor Ghorpade, over to you.
Thank you, Arun. So let me join Arun in welcoming you all to this workshop. This is, this for us was started as a small idea. Sartaj and I were approached by somebody to organize a 2-day workshop in cryptography. And we agreed to do it, and then things didn't quite work out the way we wanted them to. And then Arun came along and he said, why don't we do a workshop on, bigger, at least a 5-day workshop, and this institute would be very happy to support it. And then we decided to add coding theory and make this program. And so I just had some idea that we will call people whom we know, actually, not everybody, but at least some of them, and get them to lecture on things in this topic at a basic level that are sort of current and interesting is among interesting topics. And so we approached several people, and almost all of them said yes immediately. And the result is in front of you. I mean, when we began doing this, we thought maybe we will have about 40, 50 people, after all, by the time the program crystallized itself, we could only give about just a little over a week's notice to people to consider participating in this workshop. And we were absolutely overwhelmed with the response that we got from across the globe. And as Arun mentioned, we have close to 400 participants from all over the world. And of course, I understand why this is happening. This is happening because of the kind of speakers we have. I mean, so my very special thanks the speakers. We have 12 speakers from 6 countries, and I will be sort of saying something about them, or maybe Shabdaj or Arun will say something about them before their first lecture. But you know their names, and they are there on the website and so on. And I can tell you that it's a very a combination of young and senior people, and we are kind of fortunate that all of them have agreed to join us and lecture in this workshop. The workshop couldn't have taken place without the active support of a host who was genuinely interested in the cause. And through Arun Patel and his colleagues, we found such hosts. So it is my pleasure to mention my special thanks. To begin with, Professor Manish Kopre. Manish Kopre is the coordinator of the Center for is the coordinator for Center for Signals.
Center of Excellence, sir. Center of Excellence in Signal and Image Processing.
Center of Excellence for Signals and Image Processing, and also the PI of the TechWit project at CBS. This is the joint project of World Bank and the Government of India, meant for enhancing technical capabilities of institutes across the country, at least. They were very happy to support this venture, and I want to express my special thanks to him. I just want to say a few words before I request Professor Kopre to speak. As I just mentioned, he's the coordinator of the Center of Excellence in Signal and Image Processing. He's a professor in the Department of Electronics and Telecommunication Engineering of the SGPS Institute at Nanded. He's also connected with IIT in the sense that he did his PhD from IIT Kharagpur with Professor Bishwas and a postdoc from UC Santa Barbara. And he has wide interests, including wavelengths, image processing, recognition, computer vision, and so on. He has received many awards, including Career Award from young teachers, fellowship from the Department of Science and Technology from Government of India, and he's an active researcher who has published widely and visited various institutes across the globe. And with these few words, I invite Professor Kopre to just address the inaugural program and say a few words, please.
Thank you, sir. Thank you very much. Honorable Padma Shri Professor Bimal Roy, Professor Ghorpade, sir, Professor Yashwant Joshi, Honorable Director of our institute, Dr. Arun, Head of the Mathematics Department of HGS, all distinguished speakers and all dear participants. I'm very happy that we got a very good response for this international workshop from all over the world. Okay, the response is really good. I'd like to tell about something about Center of Excellence. This Government of India has established Center of Excellence all over India. So in 2003, Government of India called the proposals for establishing the Center of Excellence. So there were 200 proposals. Out of 200 proposals, they shortlisted 30 best proposals, and we were one among them. And under that, we got 5 crores funding in Indian rupees. And then we have established a state-of-art Center of Excellence in Signal and Image Processing, and also that is extended to machine learning and AI now. And under that, various activities we have conducted in past, like as organizing international conferences, national conferences, short-term training programs, and workshops. Nearly 40 different activities we have conducted. Recently, in the month of December, we got extended funding. Actually, MHRD has selected 4 COEs all over India, and we are one among them who got extended funding of 2 crore rupees for doing the other activities. So under this funding, we are organizing this international workshop on cryptography and coding theory. And The main outcome of the Center of Excellence, actually, I'll mention 4 outcomes of the Center of Excellence in last 3-4 years. We have basically created an Indian diabetic retinopathy database, which we have named as an IDR-ID, and this is accepted as an international standard database. And we were invited to conduct online challenge at ISPI, International Symposium on Biomedical Imaging at Washington, D.C. So in 2018, we have done that one. Then another group of our Center of Excellence is working on brain tumor segmentation along with Tata Memorial Hospital of Bombay. And we have developed a very accurate model for survival prediction of the person who is suffering with brain tumor. And then we participated in the international challenge at Spain in September 2018 in MICAI conference. And then we stood third there out of 64 countries who were participating. So that is our second contribution. Third one is like, okay, we are also working on Indian driving data set. And then, we participated in the challenge of Indian driving data set, which was organized by IIIT Hyderabad. And we stood first all over country. And recently, we have created another database of this one, multi-disease database of diabetic retinopathy. This is also accepted for conducting the challenge in ISPI 2021 at France. So our team will be conducting that one. Apart from that one, we have published so many papers from this Center of Excellence. We have good citations. More than 10,000 citations are there for our research. And many researchers are doing work. Presently, 15 researchers completed their PhD and joined industries, and 15 are working towards their PhD. So this is all about our Center of Excellence. We are focusing on machine learning applications of this one for biomedical signal processing and image processing. So that is what we are. So thank you very much. And once again, I congratulate the entire team for taking the efforts for organizing this truly international workshop. And I'm sure that this will be really fruitful because speakers are really eminent speakers all over the world. So thank you very much, sir.
Yeah, thank you, Professor Kokre. We really appreciate your support. And now I want to just invite, and before that, let me introduce Dr. Yashwant Joshi. He's the director of the institute where Professor Arun Patil and Professor Kokre work, the SGGS Institute of Engineering and Technology at Nanded. Before joining as the director of SGGS, he was a professor in the same institute in the Department of Electronics and Telecommunication Engineering. Professor Joshi also has an IIT connection in the sense that he graduated from IIT Delhi, in fact, under a renowned Indian scientist, Professor S.C. Datta Roy. He has been the director of Walchand Institute of Engineering, Sangli, for 5 years, and he is a member of various committees of the All India Council for Technical Education, Department of Science and Technology of the Government of India, and also DTE of the Government of Maharashtra. He's a member of IEEE and a life member of Indian Society for Technical Education. His interests include systems and signals, adaptive signal processing, and he has guided many PhD and MTech students. So besides being busy with administration, he's an active researcher, and I think he's known to be a great teacher. So he's indeed a key person for the development of this institute, and I would now invite Professor Joshi to say a few words, please.
Thank you, Professor Ghorpade, for introducing me to the audience. Let me start with, first of all, thanks to Professor Ghorpade, Dr. Arun Patil, and other organizing team for organizing this international workshop with the support of Technical Education Quality Improvement Program, Center of Excellence funding. For the information of all the audience, I just would take a few minutes to introduce this institute. This institute is established in the year 1981 with only 2 courses, electronics and instrumentation, with a meager capacity of 60. Now, in the year 2004, it became autonomous, and at present it runs 10 undergraduate programs of engineering, including the conventional ones, civil, mechanical, electrical, electronics, computer science, IT, instrumentation, production, chemical and textile. So almost all the spectrum of engineering is covered in the undergraduate education with an intake of approximately 700. The institute also runs 10 postgraduate programs in almost all the disciplines of engineering. It's also a recognized research center leading to a PhD degree of this Swami Ramananda Tirtha Marathwada University. This institute has participated in the prestigious Technical Education Quality Improvement Program of World Bank assisted MHRD project, now Ministry of Education. The institute was ranked 89th in 2015 under NIRF. This institute is recently in 2020 ranked 4th all over the country in the government and government aided institutions in the ARIA ranking, Atal ranking of innovations achievements. So it was 4th amongst all 128 government and aided institutes which participated into the ranking framework. We have the various laboratories which are industry sponsored laboratories. We have a strong instrumentation department wherein the process automation and process control laboratories are sponsored by companies like Emerson and Endres Hauser. Electronics, yes, the department has Center of Excellence in Signal and Image Processing, where about 20 PhDs in the interdisciplinary areas, from civil to mechanical to electrical to electronics to instrumentation. All the people are working in various domains of signal and image processing. The institute is a completely government-aided institute, and we admit only students on the basis of Government of Maharashtra merit, and it is through the centralized admission process of Government of Maharashtra. As Professor Patil has said, that this place we although have locationally slightly disadvantaged. Therefore, the placements are not to the tune like these in the institutes of which are city-based. We are almost 50% is the placement rate of the institution, and many of the students are going for higher education in the world. With this, I once again thank Professor Patil for giving me the opportunity to speak on this occasion, and thank you all. Thank you very much.
Thank you, sir. Thank you very much. So, last but not the least, I want to briefly introduce the chief guest for this function, who will also, in a short while from now, be our first speaker, Professor Bimal Roy. Professor Bimal Roy probably doesn't need an introduction to the gathering, especially of cryptographers. Also, if I start telling you things about him, I'm afraid I will take much longer time. So I'm just going to say, I just mention a few things in brief for those of you who may not have known him. Professor Bimal Roy is one of the leading figures in cryptography in India. He is currently the head of the R.C. Bose Center for Cryptology and Security, which is a center of Indian Statistical Institute, Kolkata. Previously, he was the director of Indian Statistical Institute. He is also the chairperson of the National Statistical Commission of the Government of India. In terms of academics, Professor Bimal Roy did his PhD in combinatorics from University of Waterloo in Canada. Prior to that, he did his BStat and MStat from ISI Kolkata. And he has, as I just mentioned, held many positions at ISI, as well as he has been visiting faculty at State University of New York and other places. He's a fellow of the National Academy of Sciences. He's a fellow of the Indian Society for Probability and Statistics. He is also known for his teaching. He received a Teachers Award from the Indian National Science Academy in 2014. The Government of India gives these special civilian awards, and he is a recipient of what is called Padma Shri, which is a major honor given by the government in the President of India. He contributes to the profession in many ways. He has been chairman of the steering board of Indo-French Center for Applied Mathematics, member of the Scientific Council of the Indo-French Center for Promotion of Advanced Research, and many other committees in India and abroad. So, we had an idea that he may not agree because he's usually very busy. So I thought I'll at least invite him to give one lecture. And to my surprise and pleasure, he immediately agreed and also agreed to sort of address this inaugural program. So thank you, Professor Bimal Roy. And I now request you, Bimalda, to say a few words, please.
Okay, thank you, Sudhir, for this very nice and very long introduction. And as I said, that time is actually never a constant. So you have to just have the right attitude to utilize your time. So I didn't dare to say no. So I agreed. The only thing I told that I have a class to teach at 3 o'clock today, which I don't want to miss. So I have to leave at 3 o'clock. So this is something that I don't want to miss.
Yeah.
And that's what is my profession and I enjoy the most. I just tell one thing in this workshop, because cryptography and coding theory, and you mentioned that I am now heading the R.C. Bose Center for Cryptology and Security. I'd like to mention about this person, R.C. Bose. The people who have done coding theory, they know it by name. R.C. Bose started his career as a physicist, and then as a statistician, then as a mathematician, and then he's one of the leading coding theorists internationally. He and his students, D.K. Rai Chaudhary's code, BCH code, has made them into this global arena. And even today, most of our mobile phones, they use this forward error correction while voice communication. They use the BCH code, which they have invented late 50s, 58 or 59. That is the power of this thing. So when it's a coding, I couldn't stop myself talking about R.C. Bose. And also, he has introduced in a little subtle manner. At that time, cryptology was not really there, but he was working on Shannon's notion information theory also. And in a sense, this couple of papers talks about the notion of hiding information using codes, which now I see has come big way as in this post-quantum arena. So when the government of India told me that they want to set up a research center dedicated for cryptology, then I said, okay, it's fine. I would like to host it in Kolkata, and at least for a few years I can also lead that one before it matures. But I want the name to be the name of Professor R.C. Bose, and the government immediately agreed. So all this post-quantum cryptography that we see, I think the root is basically in R.C. Bose's early work on how security could be achieved using codes. And for coding theory, he is a pioneer name. It's very relevant. So I take pride to be in a place in his name. And since I'll be talking in my talks, I don't talk anything more right now. I will be talking about the recent trends in this domain. I'll give kind of overview, because in 1 hour, if I have to cover, I think I've thought of 3-4 areas. I want to justice to the deep extent, but I'll tell you overview. And I'm very happy the students or the researchers, if you want to interact with me on a later date, you can share my email ID. And I'll be more than happy to interact with any student through email. With this, I thank the organizer once again, and I'm looking forward to very successful and very effective international workshop on this theme, coding and cryptography. Thank you.
Thank you. Thank you very much, Bimalda. It's really appropriate that you say something about the great R.C. Bose. I myself have great regard and appreciation for his work. So just to end the program, I now request our third organizer, Professor Sartajul Hassan, who is, I think, currently sitting in Jammu, to propose a vote of thanks. Sartaj, please.
Okay, thank you so much. First of all, a very good afternoon to all of you. As a co-organizer of this workshop, I'm here to offer vote of thanks. So let me first begin by thanking Professor Manish Kokare, who is the coordinator of the Center of Excellence in Signal and Image Processing. And also to Professor Yashwant Joshi, who is the director of Shri Guru Gobind Singh Institute of Engineering and Technology, Nanded, for sponsoring this workshop and I must say that without their generous financial support, it would have not been possible for us to organize this workshop, that too in such a short span of time. So we really thank you, sir, for your support. We would also like to sincerely thank our chief guest, Professor Bimal Rai, who's also Padam Shri Professor Bimal Rai, who has agreed to accept our invitation, and who has also agreed to grace this, in this inaugural function. We are really thankful to you, sir, for your time and support. We are also thankful to IT cell members, Professor Hemant Ambulgekar, Professor Ganesh Pakle, and Dr. Milind Gaikwad for providing us with all possible logistic support, such as Google Meet link, YouTube live streaming, and other technical support towards organizing this event. I would also like to take this opportunity to express my deep gratitude towards Professor Sudhir Ghorpade, who has shouldered the complete organization of this workshop. And of course, without him, it would have not been possible to organize this workshop. That includes, for example, inviting great speakers for this workshop and getting their acceptance in such a short span of time. So we are really thankful to you, sir, for your support. We are also fortunate to have eminent resource persons for this workshop. And we would like to thank all the speakers of this workshop who have agreed in such a short notice. And because of them, actually, we have seen such overwhelming response from the participants. I'm sure that the participant will get a great experience by attending lectures from masters in the subject. We are really thankful to all the speakers. I'm also thankful to the participants of this workshop who have registered. So as already mentioned by Professor Ghorpade and Professor Arun Patil, that we have now close to 400 participants who have registered for this workshop. And of course, without their participation, workshop would have no meaning. So I would like to thank all the participants of this workshop. I once again thank everyone whose contribution we might have forgotten to mention, but they have contributed. So we would like to thank them all whom we could not name here or whom we have missed somehow. We would like to thank all those who have helped us in some way or the other to organize this workshop. And I don't think we have time. I think within a minute, we are going to have our first lecture by Professor Bimal Roy. Thank you so much.
Thank you. And thank you, everybody. So we have 1 minute break, if you like, or 2 minutes. And till that time, I think Professor Bimal Roy will maybe try to share his screen. No,
I'm not using any PPT.
Okay, wonderful.
So we can have a 1 minute break and then we can, so people can join.
1:59. So yeah, we'll start at 2 o'clock. And we will really start at 2 o'clock. And that's, by the way, will be true in general. We hope to start and end in time. Especially this first lecture, we just heard that Professor Bimal Roy has a class at 3. So he might want to finish at 3 minus epsilon or whatever.
Okay, it's 2 o'clock now. We can.
Okay, so we can start. Maybe.
So I think I've already introduced Professor Bimal Roy, and it's my pleasure to invite him to talk about some issues in cryptography. Bimal.
Okay, thank you again. So as I thought, I'll talk about probably 3 very relevant topics of today in this domain of crypto, which I think there are many relevant problems, important problems. I'm talking about my perception. And which I'm also kind of working with my students. The first problem is what you call data masking or data obfuscation. Now, a little background of it. We have been working on this for quite some time. In fact, my student who did PhD on this mask and obfuscation, she is now colleague of Sartaj at IIT Jammu. So I'll go back a year and a half, and when I had the opportunity to meet our Honorable Prime Minister in person, I was appointed the chairman of the National Statistical Commission. So in a sense, I report to PM directly. I'm supposed to advise him on the matter of the data, the Indian government data. And whenever he needs some query, I am supposed to provide it to the government. So he was telling me that what he's expecting from me from this position. So I explained what he's expecting. And then then he said, what do you expect from me? Then I told certain things, a little bit less bureaucracy, access to blah, blah, blah. But then I gave him a proposal. I told, sir, you are talking about non-Indians will understand, I have translated in English. You are giving a campaign for Swachh Bharat. So this is clean India. And government is working on that towards Swachh Bharat, so to make India clean. And then I asked him, sir, except for the information that relates to national security and defense, why don't you publish all other Indian information on a public domain? So why can't we be a transparent information portal? So I was telling him, we could just give Swachh Tathya, so that means transparent information. There's nothing to hide. So why don't we make all the information public? And I didn't know, he's absolutely smart. So he told me that वो तो ठीक है, लेकिन privacy को क्या होगा? So what it means that, well, that's all right. Any information about the Indian government or the other activities, I have no problem in making it public, the citizens. But what happens to the notion of privacy? So something like if I have taken a loan from a bank and if I'm a defaulter, can anybody publish my name? The answer is no, because that is my right to privacy. So he was telling me, privacy, okay, what happens to the notion of privacy? So we have actually formed a task force in the government. Okay, we are examining the data of each and every ministry or department and trying to see if we can suitably mask it, and we can give either a proof or a strong explanation and demonstration that after masking the data, the privacy is not compromised. It is completely protected. Okay, then we could actually recommend the Prime Minister that we can publish the data in this fashion, and privacy is not going to be compromised. So we are working at the government end, and if anyone wants to put any idea, you can go to say you think of the banking information, the transactional information. Okay, this is available. So there are millions of financial transactions happens in all the bank branches. Now, how do we publish it? For what purpose we publish it? And can we keep it kind of privacy preserving? So is it possible? So if anybody can think of the Indian idea of this data, what kind of data we want to publish, but privacy is not going to compromise, I most certainly welcome it. So you can send me a mail if you have any thoughts on that. So just to mention one method for this, or since this is an interactive level talk, I normally give this example to my students. So maybe it may not be all that, it's elementary, but I think it should just set the motion of what I mean by this privacy. So there are two kinds of privacy. One is the data and one is the identity. So I don't want my identity to be disclosed. At the same time, I may not want my information in its actual form to be disclosed either. There is the data privacy or the identity protection. There are two issues. And how can we protect both of them at the same time? Still being able to give information, useful information to the citizens. But this is a challenge. So this example is very favorite example of mine. I think I gave it in my IIT Jammu talk. I also mentioned about this example to the students. Maybe I should just reiterate just to see what is meant by data privacy, what is meant by identity protection, and how can we protect both of this. So this is something which I actually did it. And the others it's called dorm. For us we call hostel. So we have students. And quite some time back, when I was the in charge of the warden of the hostel, for in the Western times the dorm in charge, I learned from some student that many students are actually drinking alcohol in the hostel. It's not that I mind, personally, it's adult people that come to the college and they're all over 18. Our Indian law does allow drinking at the age when you cross 18. So who am I to object? But there is a government rule that in the hostels, alcohol is strictly still permitted. And now it's even more, because in our time it was only alcohol, but now even smoking is not allowed. So in the institute, hostels or dormitory, neither smoking nor liquor is allowed. So that time it was only liquor. So I got this some scoop information. And since I am the in charge of the hostel, whatever the hostel, I have to find out, is it so, how bad it is. And then I have to recollect my time. So in my class, we were 28 people at ISI. And 3 of them had this habit. Okay, I'm thinking of my plus 1 plus minus 1 year. My plus 1 year, there are about 32 students. In ISI, it's typical, we publish a list, but there is no second list, no waiting list. Whoever doesn't join, we can fill it up. So the strengths are normally 30 plus or minus. We normally admit about 40, but people have choice to go to IIT or medical. So many of them ultimately join, but the number of seats we don't fill up. So there were 32. Again, I remember some 4 or 5 of them had this habit. My next batch had an even smaller class, maybe 23, 24. About 3 of them had this habit. So if I think, so there are some 10, 12% of my students had this habit even in my time. Now, time has progressed, people become more within progressive. So number might go up. Now, to what extent? If it is 15, 20%, I think I better not bother about it. But if it's 40, 80%, then maybe I should bother. So I have to find out what percentage of my students in the dorm or the hostel, they drink alcohol. Anyhow, if I ask a student, do you drink alcohol in the hostel? What answer do you get? The person even may get angry. But why do you ask me such nonsense questions? Or somebody may simply refuse to answer this question, which they're right, and getting into their privacy. Or even if somebody becomes very polite and answers it, the answer is correct. It's not that probable. That we all understand from intuition. So asking the students and find out what percentage of my students are drinking alcohol in the hostel is out of question. This is not feasible. So we learned in our statistics course in our when I was doing my undergrad here, something called randomized response. So I adopted that method. What is that method? So I told my students, well, I know if I ask this question, you are not going to cooperate with me because you think this is getting into privacy, which I'm 100% sure you are right. So let me ask you a different way, a different question. It's like playing a game. I ask you 2 questions. Question number 1, you drink alcohol in the hostel? Answer is yes or no. I put a second question. Are you born between January 1 and June 30? Are you born between January 1 and June 30? Okay. Even the answer to the second question is yes or no. So then I ask my actual part of the game. So you take a coin and toss it. If it is head, you answer first question. And if it is tail, you answer second question. And don't tell anybody on earth about the outcome of your toss. And then you just write Y or N on a capital, just Y or N on a piece of paper, fold it and leave it on my table. Okay, the game clear? Question 1, do you drink alcohol or not in the hostel? Yes or no? Y or N? Are you born between January 1 or June 30? Answer is yes or no, Y or N. You toss a coin, if it is head, you answer first question. If it is tail, you answer second question. You write the answer either capital Y or capital N on a piece of paper, fold it, leave it on the table. So, will you play this game? Okay, and then what the students were thinking at the back of their mind. So, I will ultimately get a bunch of yes or no, Y or N. Now, from this bunch of this piece of papers, can I guess whether a particular student drinks alcohol or not? If they feel that I can guess, then they will think I'm getting into the practice. But if they think that I cannot guess, then they may like to play the game honestly. So how do you think? Now, number 1, the data privacy is Y or N. What I'm writing? Y or N. Okay. So I think this is the identity protection. Y or N. Now this is only one single capital letters. Now you ask any handwriting expert from just a single capital letter, Y or N. Can you guess whose handwriting is this one? Okay. The answer is no. You ask any expert. No one can guess from just one single capital English letter whose handwriting is this. So this is, so my identity is protected. From this Y or N, I cannot know whether my identity is revealed. So my identity is protected. Next we have a data. Now, I don't know what is the outcome of your toss. So I don't know which question you have answered. Okay. So from this Y or N, I don't know what is your actual data. So that is like data protection. So I have ensured your identity privacy. No, I cannot guess who has written which piece of paper. And inside the piece, the data is there. I don't know from the data what is the actual information. So I don't know the outcome of the test. This is a very classic example to establish the idea of data privacy and identity issue. And then how do I solve my problem? I want to know what percent of the students do take alcohol in the hostel. So it's very simple now. I had some 400 piece of paper. One student responded, and I got 132 yes, capital Y. So 400 answered and 132 capital Y. So let me just go back a little bit of my elementary school arithmetic, a little bit idea of probability. So since for head, the student answered the first question, for tail you answer the second question. And if I assume that my coin is unbiased, although I have no way to judge whether a coin is unbiased or not. Also, I have no way to make one coin which is unbiased. Okay, so the notion of unbiasedness is very, very difficult. I heard that the quantum machines can generate a binary string where 0 and 1 are exactly, it comes in probably exactly equal. But our traditional method, I don't know how to simulate an unbiased coin or generate an unbiased coin. But assuming that the coin is unbiased, so of the 400, 200 will answer yes. And 200 would answer no. Very simple. I mean, a strong assumption because they are unbiased. Look at the second question. Are you born between January 1 and June 30? Now, if I assume, again, an assumption that the births take place uniformly over the year, and that is half the year. So, of the 200 students who answered second question, half of them would answer yes. So, 100. So, I would expect 100 of them would answer yes. But then comes the rest 32. I got 132 yes. Out of 100, out of the 100 yes came from my second question. So 32 yes must have come from the first question. 200 of my students answered the first question, and I got 32 yes. So this means 16% of my students do drink alcohol in the hostel. And this is not much than my time. It was 15%, 16%. So I didn't bother to take any administrative action, which are normally counterproductive. So this is a classic example of how do we hide or mask the identity as well as the data. So we are in a position to make a government policy where for every ministry's data except security or defense-related data, if you want to make public, how are we going to, what kind of algorithms are we going to use so that information I don't lose, but I can protect identity as well as the data. So this kind of, this is a challenge. Well, we are getting solutions, but this is one of my national job as the chairman of National Statistical Commission. Anybody wants to work on this, most welcome. Okay, next I go for my second problem. So the second problem, again, there is a motivating story about the second problem. So this is about this, this bank lockers. Some 2-3 years back, I read a news item on the newspaper that a couple went to a bank. So they had a bank locker, and in which they used to put their valuables and jewelries. And the lockers normally have 2 keys on the 2 sides of the locker. 1 key is held with the customer, and 1 key is held with the bank. So they have demonstrated that when I go to the bank, with 1 key the locker doesn't open. When I put both the keys together, the bank's key and my key together, and when I turn it, then the locker opens. Okay, so seemingly this is very safe and secure. But then this couple one day just discovered that their locker is empty. So they run to the bank manager and say that we have to pay fee for this rental for this locker. So how does everything gets lost from here? And the manager says, how do I know? Because with my key I cannot open it. And he shows that my key can't open it, so I'm not responsible. I cannot do anything. So the manager refuses to intervene in the matter. He says, no, it's your problem. The bank cannot get in this problem. Then they go to police. That they've lost it some crores of rupees. So the bank manager, so the police comes and meets the bank manager and makes an investigation. And the bank manager tells the same thing. And the police also says that with the bank manager's key, it can be opened. So police doesn't dismisses this case. That the bank is not at fault. Okay, then we go to the court. In the court also, the court gave a verdict in favor of the bank. But they gave a verdict on a very different argument. I think the judge did the right thing. the judge asked this couple, did you make a list of articles that you are going to put inside the locker? They said, no, there is no such convention. He says, if you don't make a list of articles that you are being put inside the locker, unless the bank verifies it and puts a second swipe, put another signature, because then everybody will come, will empty their locker and tell that the bank has taken it. So unless this system is in practice, the bank cannot be held responsible. So this one was against the couple in favor of the bank. So this was reported in the newspaper, and then it tickled my mind. I was a bank locker, so I went to my bank. Okay, and I asked the manager. The manager, I have got 2 questions. He said, okay, tell me. My first question is that I have studied, I have been as a hostel or in the school days, I was in a boarding school. So I used to put all my belongings to a desk or an almirah, and then I used to put a lock. That time it was a click lock. I put it and then lock it. And then after a few days, I lose that key. What do? I don't cry or I don't shout. I go outside the campus and there is an old person, a locksmith sitting. So I call him. He comes with pudding and he'll put the pudding on that lock and get the impression of that lock inside. And then in 5 minutes, he used to reproduce the key. Amazing. And I have never suffered because I lost my key. So I asked him a little technical question, manager. Do you have any reasonable explanation or maybe a proof that my key cannot be reconstructed? And then he says, oh, what do you say? What do you say? How do I have a proof? I don't know. If you cannot give me a proof, then I don't feel secure. I need a proof that my key cannot be reconstructed. As I have seen from my school days, college days, that the key that I used for my locks would all be reconstructed by the locksmith. So the proof that this is not reconstructed. Then I put a second question, which actually floored the manager. My second question is, what you have shown me that this pair of keys, my key and your key, opens the lock. Now I want a proof, a reasonable explanation that there exists no other pair of keys on earth which can open this lock. I repeat the question. There exists no other pair of keys on earth which can open this lock. And then the manager is almost floored. And then says, Professor, you just explained, I have no answer to you. Please just leave me alone. So I come. And then I wrote an article on Times of India about my concern. And I should say that I did not implicate, I didn't imply that these lockers are unsafe. I don't, maybe they're very safe. But still there must be a formal way of establishing my concerns. That is the notion of security. And what is that? Now, if I put into a cryptographic domain, this is something like a key for an encryption, which is not held by a single person. This for security is only. So there is something called a number of participants. So I could think of something like a scheme, like I have got some important information which myself, Sartaj, maybe Prakash, and Shudhir. Okay, we four will have access to information, but either me or Prakash and Sartaj or Shudhir, they should be able to access that key and no other pair, nobody else. So meaning that Sartaj and me could reconstruct the key. Sartaj and Prakash could reconstruct the key. Sudhir and me could reconstruct the key. Sudhir and Prakash could reconstruct the key. But me and Prakash would not be able to. Sudhir or Sartaj would not be able to. Now, can I share a key for this application? Now, this gives rise to a very general problem in cryptography. This is called secret sharing. So, in general, secret sharing means you have a secret, it's shared amongst a number of participants, and then you define certain subsets of this set of participants. Like here, my participants are 4 of us, Sartaj, Sudhir, Prakash, and myself, and we specified 4 subsets. Okay, Sartaj and me, Sartaj and Prakash, Sudhir and me, Sudhir and Prakash. These 4 subsets. They are bona fide, they are eligible to reconstruct the key. That means I must have an algorithm from, there are two algorithms. One algorithm is that from the key, I should be able to generate 4 keys, which I call shares. Give it to 4 of us. Okay, and then I have to show that if I get this bona fide subset, or I say qualified subset of any of these 4 subsets, if they contribute, they are shared, and there's an algorithm to reconstruct the original key. Now this is a very applied problem. It's general secret sharing, and it has been shown that the general secret sharing problem, as of today, is computationally hard. I would say that we have proved it to be NP hard, but it's computationally hard, meaning that this becomes exponential in the number of members in the number of qualified subsets. So, which is huge. If the number of qualified subsets grow, it's huge. So, what we try to do? We try to identify some class of qualified sets. Okay, and see for that set of qualified subsets, can I get an algorithm in what we say polynomial time? You can reconstruct the key. So that's a challenge. That's a very current. And for doing this, how can I actually do this and in a very efficient way? So I had one student who just finished PhD in this domain. He was a mathematician. I remember I learned when I was a PhD student about Waterloo, metroid theory. The metroid theories are basically that unifying the idea of forests in graph theory and independent sets in a vector space. So they are kind of unifying these 2 theories, and they define a concept called metroid. Metroids are basically, in metroid also we have got a set and a class of subsets having certain properties. Okay, and there have been work in this direction that if your set of this qualified subsets, okay, if they evolve from some metroid, we expect that I should be able to get a good secret sharing scheme. Okay, now this is more complex than that, but in a sense that we are trying to map or understand the set of qualified subsets. Does it evolve from a suitable metroid? So like this, in this case, if I could see that, what I told, I have got 4 participants, Sartaj, Sudhir, Prakash, and myself, and what the qualified sets, Sartaj, myself, Sartaj, Prakash, Sudhir, myself, Sudhir, Prakash. Now, does this set of subsets, can it be evolved from a metroid? If it is, then I do expect, it's not guaranteed, but I do expect that I will get a very nice and a very kind of polynomial time, a very nice secret sharing scheme. So we are linking metroids in the secret sharing scheme. This is a new attempt, I think, not more than 10 years. We have been working on this area, and this has become a very popular method. So mathematicians who like graph theory, vector spaces, linear algebra, these concepts, one can study metroids, and the metroids will have a direct application to constructing the secret sharing scheme. Yet this is far from being resolved or solved. Problems comes and problem comes, more and more problems. You have plenty of problems to look into. You can make a good result, good paper out of this concept. So this is linking metroid and secret sharing scheme. So I'm not getting the mathematical details. If somebody wants, I can email you the hot paper on what we have done on this metroids and secret sharing scheme. But by and large, from metroid, this if I can involve this set of qualified subsets, then we expect that we will get a good algorithm. This is the nutshell. Okay, the third and the last problem that I want to talk about. This is also this emerged. I think I got the idea from newspaper. After some, I think in some election, in election we use EVMs, electronic voting machines. So we go and press the button, and my vote gets stored in this memory of that EVM. And after the voting is complete, this machine is kept under the custody of the returning officer. And on the day of the counting, they are going to open this machine and read what is there in the memory, and that will they're going to count the number of votes each candidate gets. I saw again in the newspaper some years back, 14 parliament election. Our Honorable Arvind Kejriwal ji was making a complaint that the votes are actually changed. So after the vote was cast, okay, it has been put into the memory of the EVM, and before the counting starts, there could be, if the government wants, they can always manipulate the memory, and the memories are actually compromised, and the votes are all compromised votes. This is what, or he even complained that even the other way, that even while voting, you think you are pressing the button to a certain candidate, because then there is a VVPAT machine, so there will be a symbol of that of your vote appearing in any piece of paper, and you are happy that this is the vote there. He said a school boy can actually construct a machine where you input something, output is shown, but something else goes to the memory. We can do that. It's possible. So I remember Arvind Kejriwal is a IIT Kharagpur BTech graduate, very smart man. So he made this complaint. And then election commission, through a challenge, that he proved that this machine is not proper and this can be compromised. And then Kejriwalji wanted, I don't know the machine, he just give me the circuitry, the drawing of the circuitry, what we have done. And the election commission refused to give the design. And then he refused to take the challenge. He says, unless I get the design, using a black box, I cannot prove this is good or bad. But still, even now I hear that if somebody loses the election, they say that it is due to the EVMs. EVMs are improper. Okay, so they have this question. So I met the current Deputy Election Commissioner, Sunil Jain. Absolutely smart person. He's also from IIT graduate, then he became IAS, and from IAS service he deputed as the election commission. And I was chatting with him, and I told that I would like to believe, or maybe I believe, that all the EVMs are perfectly all right. But then it's also onus on you to prove to the people or convince people that these machines are behaving properly. So while I'm not questioning that this machine is improper, but I insisted that we have the onus to prove to the community that these machines cannot be compromised. And then he said, well, if we can come out with a model, and then I'll be very happy to look into it. So I started working with the PhD student of mine. His PhD 5-hour defense is just day after tomorrow. So he has supposedly designed an end-to-end verifiable e-voting system. So this is, so I'll talk about some aspects of this e-voting, and then I'll conclude, and probably I'll leave maybe 10 minutes for questions. So what are the issues here? The first question is my authentication. So when I go for voting, when you think of the voting pattern, I take the voter's ID. The ID, I have my picture, I have my name, I have my signature or my thumb impression. So as a polling officer, to whom I give this my voter ID card, and also in his record, he has got a printout of my voter ID card. So he has also my picture, my signature, my name and card. So he will take my voter ID card. He will try to look at the picture in my voter ID card. The picture he has got a printout from the election commission and looks at my face and tries to make sure that these three are the same person. And then he asks me to sign or put the thumb impression. And then he has on his printout some signature or thumb impression. My voter ID card has my signature or thumb impression. And then in person I put the signature or thumb impression. Then he tries to tally these three. And he makes a judgment whether I am the person. Okay. Now, with all due respect to our government procedures, you just look at your picture at the voter ID card, and if you take another printout, and if you look, matching these three is very difficult. Matching signature is difficult, but matching thumb impression is out of question for the polling officer. There is a thumb impression on the voter ID card, and I put a thumb impression to the polling officer. There is thumb impression printout from the election commission to the polling officer. Now he's trying to match these three. Who on earth can do it visually? The thumb impressions, these three are matching or not, same persons? I don't know. Any expert who can do it. So this voter authentication is actually not proven. Not proven. Again, I must re-emphasize that I'm not telling that voters are impersonating, even though here in the newspaper it happens, impersonation. But even if there is no impersonation, but this is not a way to establish that I am the voter. So there must be a way of me establishing that I am the right voter. So how do I prove myself? So biometric may be a way. That's what we're thinking of. But then I want to prove to the polling officer that I am the same person, but he will not have a knowledge of my biometry. You know, if he takes, I don't want him to gain any knowledge about my biometry, because you can actually make foul play with my thumb impression, or with my signature, or my thumb impression, or my iris and etc. So I want to prove to the polling officer that this is me, even though I was come to vote, but without giving any knowledge of this, my biometric details. Okay, so how do I do it? This is what we have technology now, or method now, zero knowledge protocol. So zero knowledge protocol gives you a methodology to prove that you possess something without revealing any information about what you possess. Okay, so let me give an example. This is also one of my favorite example that I give to the even I tell it to school students. That, what is this notion? I claim that I have something, and I prove to you that I have something, but you will gain no knowledge about that something. Okay, this is my classic example. If you play Sudoku, you know what I'm talking about. But those who do not play Sudoku, let me talk about the game. A Sudoku game is there's a 9 by 9 square. Okay, so 81 small cells, and they put some digits 1 through 9 on certain cells, and then you have to fill up the other cells in such a way that each row must have all the digits 1 to 9 exactly once. Each column will have all the digits 1 to 9 exactly once. And there are 9 3 by 3 subsquares. If you can think of 9 by 9 square, we have 1 3 by 3, another 3 by 3, another 3 by 3, 3 by 3, 3 by 3. We have got 9 3 by 3 subsquares. Each of the subsquare must also have all the 9 digits 1 to 9. And if you can fill up the rest of the cells, satisfying these 3 properties, then we have solved the problem. So maybe I tell Sudhir, I have solved this problem. And Sudhir says, okay, show me Bimalda, you are not that smart. I don't believe that you can solve this problem. Then the one to establish that I have solved the problem, I can show the solution to Sudhir. But I don't want to show the solution to Sudhir. I'm not going to show my solution to Sudhir, but yet I will prove to Sudhir that I have solved the problem, and he would be convinced that I have solved the problem. Okay, so how do I do it? So it's a game. I've converted this to some mathematical framework later on, but these are formal things. But I think I want to set up the basic concept here that is doable. What I do, I make 81 slips, small slips. 9 of them I write on one side. 9 of them I write 2. None of them I write 9. Okay, so small slips, I write a digit. On the other side is blank. So on my solution, I cover with these 81 slips in a way that if the cell my solution has 2, I cover it by 2. So that piece of paper outside is blank, but inside is 2. So 2 on top of 2, outside blank. So you cannot see anything. Likewise, fill up this square. And then I say, Sudhir, I give you a challenge. You tell me a row randomly. So Sudhir says, row number 5. So what I do, I take those slips from row number 5. Okay, and swap it in my hand, randomize it, flip it, and show it to Sudhir. Now Sudhir has to verify that I have got all the 9 digits. He has no business to know in which order the 9 digits came. Randomize and show it. Then again I put it back, cover it. Then I say, Sudhir, you tell me a column. So this says column number 7. So I again do the same thing. I take those slips from column number 7. Okay, in hand, swap it, then I randomize it, flip it, and show it to Sudhir. And all Sudhir has to verify that I have got all the 9 digits. She has no business to know in which order it came. And then again I put them back in the square. Then I ask Sudhir, you tell me which subsquare you want to verify. There are 9 subsquares. So tell me, maybe the last corner 3 by 3 subsquare I want to verify. Then I take those 9 slips from the last corner 3 by 3 subsquare. I take this piece of paper, in my hand, I just swap it, randomize, I flip it, and show it to Sudhir. And Sudhir only verifies that I have got all the 9 digits. At this end of this process, if you want to repeat, I can repeat. But at the end of this process, Sudhir will be convinced that I have solved the problem. But will he know the solution? Absolutely no. So I have convinced Sudhir that yes, I have solved it, but without giving any knowledge about the solution, Sudhir will be convinced that yes, I have solved it. So this is what is basically the zero knowledge protocol, zero knowledge proofs. And my student has established an algorithm of zero knowledge protocol for the voter authentication. So I proved myself to the polling officer that I voted, but the voter will not get any information about my biometrics. This is the first part of the vote, the authentication. Second part, okay, when I vote, I want to make sure that my vote is actually stored. Okay, now I would have used a board, but that doesn't matter. So I just a little bit of this. How do I verify this? So I have, my student has given an option of auditing. What is meant by auditing? So the voting is like that. So you choose a random number. When you vote, you may carry a random number with you, or you can use a machine to random number, and the machine will compute. Okay, we think of a large finite group with two generators, G1 and G2. Okay, and I assume that I have got only two candidates for simplicity. For one candidate, my vote is 0. And for the second candidate, I put 1 for my vote. Okay, so what I do, the machine would compute G1 power that random number and G2 power that random number plus my vote. Okay, and I can verify. The machine is going to compute G1 power R, G2 power R plus V my vote. The machine will give back the node. Machine can put it in the public domain. Now,
Sir, you are not audible. Please unmute
You have
yourself.
to unmute.
Professor Bimal Roy. Professor Roy, can you unmute yourself, please? You are muted.
sorry, I don't know how I
Yeah,
okay. So, what should I start again?
No. It was just a minute that you unmuted.
Okay, just a minute. Okay, so I'm talking about the voting.
Yeah.
So, what I told that I like using it's a slide as a board, but then I think I can explain it. If you have some paper, you can write it down. So I have a group, large finite group with two generators, G1 and G2. So I assume that I have only two candidates for simplicity. And for one candidate, my vote is 0, other candidate, my vote is 1. So what I do, when I go to vote, I choose a random number. I can take random number with me, or I just choose random. I'm just on the spot. And then when I input my number, and I also input my vote. But then the machine will compute G1 power the random number, G1 power R, and G2 power R plus V. And this is what the machine is going to publish, and in a very public domain. Okay. Now you can verify whether your vote is recorded or not. But for somebody, from this published result, G1 power R and G2 power R plus V, no one can guess what is your V. Because if you can guess V, that is basically solving the discrete log problem. And as long as discrete log problem is computationally hard, I'm safe in publishing this one. But you can verify whether your vote is stored or not. And you may give in the scope of auditing, so you may first try this once or twice, make convinced that the machine is recording it properly, and then you say, now I am going to vote. So you may give an option of auditing also. But anyway, so if you do this one, using this hardness of discrete log problem, you can ensure that my vote is stored. Okay, then KGOL is concerned that after the vote is stored, this is compromised. The memory is compromised. So what I do, we now know blockchain, publicly verifiable blockchain. So we'll put all this G1 power R and G2 power R plus V in a public blockchain. Okay. So blockchain technology has gone quite a bit, and it's very difficult to tamper this blockchain. So I don't want to spend any time on my blockchain. So we put in this blockchain, publicly verifiable. So even public can verify that your votes are properly accounted for now. If there is any change, any compromise in this blockchain memory, it will be immediately triggered. Okay, so if I put in the blockchain, or somebody say we can put in hash chain, that will be more quick. So doing this is going to ensure that the vote, what is stored, has not been compromised during that idle period. Voting is over and the counting starts. Okay, this is what we proposed. This is publicly verified blockchain for this one. And the last part is counting of votes. These days we count the votes using this voting machines. Now, what is a voting machine? For one booth, one voting machine. That's about 800 to 1,000 voters. So people know the voting pattern in every booth. And I think this is privacy compromise. Not an individual level, but a small group level. And what the voters in a booth, they are physically located in one area. The house estate where I stay, all of us vote in the same booth. So when the counting starts, they would know each candidates how many votes they got from our housing area. And this, I think, is a breach of privacy as a small community level. And there's no reason people to know how we voted. All in know there are 300 booths in a constituency. What's the total number of vote every candidate got? Okay, so we want to publish only the sum of the votes obtained by each candidate over the booths, but not an individual value. And this is how I do it. This is do it by there is another primitive in cryptography now, secure multi-party computation. So we have used one model of secret multi-party computation. We have ensured that we don't publish any of the individual EVM vote pattern, but we will get the sum. So this altogether put, we call it end-to-end verifiable electronic voting system. Okay, and if somebody interested, we can send you the paper, and the student is actually defending his thesis day after tomorrow. I say only. Maybe I should stop here. Let me allow some 5-10 minutes question, and then I leave for my class. So is that okay?
Yeah, that's fine. That's fine. I think
okay.
So audience, you can just ask questions. Maybe you can. Yeah, there is already a question in the chat box. I see by Akash Mandal.
Yeah. What is the question? I couldn't see.
He asks, can you explain the Sudoku thing with 81 clips? How to prove authenticity that you have solved without giving the solution?
Okay. So I told it. Maybe I should repeat it once again. So I claim that I have solved it. That means I have filled up this 81 small cells with these numbers. Okay. And then what I do, I don't want to show you the solution. So what I do, I create 81 small slips of paper. Okay. And which conclusion? Okay. So on each piece of paper, I write, say, 9 of them write 111, 9 of them write 222, 9 of them write 999. And on the other side is blank. So on the board, if there is a 2 there, I cover it by a slip where 2 is written. So I cover it by this 2. So on the top there is blank, inside is 2, is covering a 2. So on my board, you cannot see anything, only blank one, but 2 and 2 inside on the slip 2 and the board is 2. That's really done. But now I ask Sudhir, I give a challenge. Okay, tell me a row. And Sudhir says row number 5. What I'll do, I'll take up the slips from row number 5. Okay, my board is here. I'll take up you will see that he cannot read what is there, but he could see physically that I have taken up the slips from the row number 5. Then what I did, put in hand, I have just randomized, and then I flip it and show it to Sudhir. And all Sudhir has to verify that I have got all the 9 digits. He doesn't know in which order it came. So he verifies that it's all 9 digits. And then I put them back again on the board. Then I ask Sudhir, tell me a column. Sudhir says, no, column number 8. So I'll pick up those slips from column number 8. Okay. Then again, take in my hand, flip them, randomize it, flip them and show it to Sudhir. Sudhir has to verify that I have got all the 9 digits. I put them back. Now I tell you, think of a small subsquare. Okay. So we choose any subsquare of these 9 subsquares. I take those 9 slips from that subsquare. Okay. Again, I randomize and I flip it before Sudhir. All he has to verify that I have got all the 9 digits. Then I put it back. So I can do it over no one. But after some time, Sudhir will be convinced that I have solved the problem. But will he know the solution? No. There's no way to know the solution. Okay. So this is the thing I was trying to apply to the voter authentication. I should be able to prove that this is Bimal Rai to the polling officer, maybe through my biometrics. But I don't want the polling officer to gain knowledge about my biometry. There's something in the other. Other has a copy of my biometry, my iris, my ear, and my fingerprint, so on and so forth. So without when I was getting any knowledge of my biometry, I proved to this thing is I am the same person. This is what I have got stored in my other record also. Okay. So this is similar kind of zero knowledge protocol my student has designed. Okay, there's a second question I saw that in the voting one, this computation difficult one is a discrete logarithm problem. That when I want to verify that the machine has recorded my vote, what I did, I had my random number and I have my vote V. So the machine will compute G1 power R, G2 power R plus V. How would one guess my V if you can solve such a discrete log problem? A discrete log problem as of today is a discrete logarithm problem, DLP. That is a problem I bank upon. As long as this is very secure, I can verify that the machine is actually recording my vote. And then again also this vote goes into a blockchain, so it's publicly verifiable also. Nothing can be tampered. Okay, what are the other questions?
Yeah, I think that was it. Ritika Ganeshan said she didn't catch the name of the problem that's composed.
Yeah. So DLP, discrete logarithm problem.
So I don't see any other questions in the chat box. If anybody wants to, just unmute and mention their own questions, you're welcome. Okay, last chance. All right.
Okay, good.
Let us thank Professor Bimal Roy for this.
Yes, you are right. Right. So, but as of safe as long as there is no quantum machine.
Yeah.
So if there is a quantum machine in practice, this will be useless.
Yeah. So what is now quantum machine? Quantum computer can probably add 2 plus 3 now. What is the current?
I don't know. So there are lots of claims. I'm not convinced at all. There are lots of claims, but I'm not convinced.
Yeah, so I think we are far from it in any case. Okay, if there are no further questions, let us thank Professor Bimal Roy for a very nice and engaging talks. And he has set the tone for what is going to follow. I think you probably understand better why we need to know more about cryptography, and subsequent lectures will tell you about that and also about coding theory. Thank you, Bimalda, for this very engaging talk and sort of nicely chatting with us and telling us important issues in cryptography. Thank you very much.
Okay, thank you. So I can go back to my class now. Okay, it's 3 o'clock. Yeah. Okay, thank you.
Yeah. So, and for the audience,
Professor Bimal Roy.
Yeah.
Yes. Okay, thank you.
Thank you. So I think we take a break now. I think next lecture will be at 3:30, right, Arun?
Yes, sir. Indian time 3:30.
Yeah. I mean, because the lectures are heavy, we need time to recuperate, maybe get ourselves a cup of tea or whatever.
Yes.
So do that. And in general, I have asked lecturers to use even up to full 1 hour for speaking. And if they allow, you can take questions in the buffer time if they have some free time. So we always welcome questions. You can mention them in the chat box or ask the speakers yourself. Okay. All right. Thank you very much. I think we can stop here. Maybe we can stop the recording and then we continue at 3:30.
Yes, sir. By Professor Samrit.
Yeah. The next speaker will be Professor Samrit Ram from IIT Delhi.
Okay, sir. We can take a leave, and participants can stay here or they can leave and they can rejoin back. Rejoin this.
Yeah, it is going to be the same link.
Yeah, if they wish to save the data back, they can leave and they can join.
Yeah. Okay. I'm going to leave and I'll come back.
Okay. Thank you, sir. Thank you. Good afternoon, Samrit. Are you there?
Hi, Arun. Yes.
How are you?
Yes.
So, how is Delhi, temperature-wise?
It's good. It's okay. It's beginning to get quite hot right now.
Okay. But manageable. I think May, June is quite hot.
Yeah. In fact, already post-winter, it has started to rapidly ascend. So maybe even more so than previous years. So.
So, Samrit, I see that you will write on the tablet or something?
That's right. I'll be writing. I hope it's visible, right? What I'm writing, I hope it's clear.
Yeah, right now there is, yes. I think it is visible.
Okay. All right.
Sartaj will officially introduce you.
Okay, sure.
With the chair and some sense. So although we have a large number of registered participants, the number of people who actually join a given lecture is not.
Yes, sir. In morning, the number went to 110. 110. So, hopefully, first inaugural session, they might have not done well.
Yeah. No,
Yes, sir. Yeah.
some people may be interested.
But still we have both the links. YouTube live streaming also is there, and this Google Meet also there. Some participants have requested to share their videos. I think their timings are also not matching.
Sorry?
For example, some participants requested for sharing videos. For example, Bhavin Moria, if you remember, sir, he was in HRI.
Yeah.
So now he is in Brazil. He requested me to share videos.
So videos of lectures.
Yeah, video of lectures.
Okay, that we have not decided. Of course, that depends on permission from speakers.
So that we have to ask for.
If the speakers permit us, we might share a link for the videos, but that will happen after the workshop. Okay. At the moment, we are not guaranteeing that we will do this.
Okay.
So I think it's time for the lecture. So
yeah.
Okay. So I will, as we are back from the break, and the next talk is going to be on polynomials over finite field, and this would be given by Professor Samrit Ram from Indraprasth Institute of Information Technology, Delhi. So I think without wasting much time, I would directly state for a request Professor Samrit Ram to kindly present his talk.
Okay, thank you, Sartaj. I would like to begin by thanking all the organizers and all the people who made this possible, and again the organizers for inviting me to give this lecture. So what I intend to do today in today's lecture is that I will recap some basic facts about finite fields that you would find useful later on in this workshop. So let me maybe begin by saying that if you have, let P be a prime number and R be a positive integer, And if Q is a prime power, then for each such Q, there is a unique finite field, well, unique being up to isomorphism with Q elements. And any field, in fact, such a field may be characterized as the splitting field of the polynomial x to the q minus x over fp. Okay, so I will use some basic facts from algebra about field extensions and so on. But one of the striking properties about finite fields is the fact that the multiplicative group of non-zero elements of fq forms a cyclic group. This is in fact a very useful fact. And let me begin by quickly sketching a proof of this result. One way to prove this result would be to use the structure theorem for finite abelian groups by saying that you could split it up as a product and so on. But I would like to give here a slightly, I would not like to use the structure theorem, and I will sketch proof using some properties of the Euler-Dirichlet function. Okay, so all right, so let's begin by recalling what the Euler-Dirichlet function is. So Euler-Dirichlet. Okay, so this function is defined for positive integers. So phi n for any positive integer is the number of positive integers k lying between 1 and n, which are co-prime to n. Okay, so that's the definition of the Euler-Dirichlet function. Now here is a basic property of the Dirichlet function that we will use. So for each positive integer n, we have the sum over the divisors of n of phi of d equals n. Let me quickly sketch a proof of this. One way to argue would be to say that if you could take a cyclic group of order n and count and say one could show that the number of elements of whose order is exactly d is phi of d. But let me sketch another proof, a slightly more elementary proof, which doesn't need the use of groups at all. So let's begin by expressing. So let's start with these fractions. So express the fractions 1 by n, 2 by n, and so on up to n by n in lowest terms. Okay, so write each of these. So if we do that, well, each of these will reduce to a form c by d, where d is some divisor of n. And since it's in lowest terms, the c and d must be co-prime with c less than or equal to d. So what are the possible fractions that appear with a given denominator d? So one can see that the number of fractions, this is after we express them in the lowest terms, with the denominator d is simply phi of d. This is because every fraction, so for sure fractions of the form c by d will appear where c and d are co-prime, but also every such fraction will appear because I could also express a fraction of this form with a denominator n. And since all these n fractions are distinct, each of these appears precisely once. Okay, so if we count fractions by their denominator, then this simply gives us that the sum over the divisors of n, phi of d, is simply n. I hope that this proof is clear. If at some point you have, of course there will be time at the end of the lecture to ask questions, but feel free to post any queries that you may have in your chat, and I might look at it once in a while and respond. Okay, so let's get down to the proof. of the multiplicativity of the group of non-zero elements of FQ. So let me state it as a lemma. Maybe before I state this lemma, I would like to say that about the Euler-Totient function, neither the symbol phi nor the name totient are due to Euler. In fact, Euler used the Greek letter pi to denote this function, but Gauss in his book Disquisitions used phi, and that practice has continued till today, whereas the name totient was coined much later on by Sylvester. Okay, so let's get back to the lemma. So let G be a finite group of order n. If for each divisor D of n, we have the number of elements in G such that x to the d is 1. So if the size of this set is at most d, then G is cyclic. Okay, so what this lemma says, so if you look at this, those elements in G whose order divides D, and if there are at most D of them, then J is automatically a cyclic group. So let's prove this. So how could we use this? So recall that over a finite field, so we are essentially looking, if G is a finite subgroup of the multiplicative group of a field F, then we are looking at roots of the polynomial x to the d minus 1. And over a field, a polynomial of degree d can have at most d roots. So the hypothesis of this lemma would be satisfied in that case. So for each, so let's prove this. So for each divisor d of n, let GD denote the set of elements of G whose order is precisely D. Okay, so let's first assume that GD is non-empty. Okay, since GD is non-empty, we can pick some element. So let alpha be some element in GD. And if one looks at the cyclic group, subgroup generated by alpha, then since alpha is of order D, certainly all elements in the group generated by alpha will have their order dividing D. In other words, this is going to be a subset of those x in G such that x to the D is 1. So this containment holds. Note that the order of any power of alpha has to be a divisor of the order of alpha itself. So this should be true. Nevertheless, since alpha has order D, it must be the case that this group is of size D. Whereas the set on the right-hand side of this inclusion has order at most D. Therefore, equality holds in the above inclusion. In other words, the cyclic subgroup generated by alpha is precisely those elements of G whose order divides D. So then, GD must be those elements of order exactly D in this cyclic subgroup generated by alpha. In other words, so it follows that the size of GD should be equal to the number of generators of this cyclic group, and that should be precisely phi of D. This is the number of generators of a cyclic group of order D. So basically what we have shown is that this size of GD is either 0 or it is phi of d. So now what we can say, so count all elements in the group. So recall that n is the order of the group. If you count them by their order, well, the order must divide the size of the group. But also, by assumption, the number of elements of order d is precisely gd. And by what we showed, since gd is always phi d or 0, this is bounded above by the sum over the divisors of n of phi of d, which by our lemma is precisely n. So what this shows is that if for some gd, its value is strictly less than phi d, then there's a contradiction here. So what this means is that the order of gd, or rather the size of gd, is precisely must be equal to phi d for every divisor d of n. And in particular, Gn is not empty. Therefore, G is cyclic. Gn not being empty simply means that there are elements of order n, and therefore this G is a cyclic group. Okay, so the corollary to this, by our observation, by the observation made initially, is that the multiplicative group of non-zero elements of a finite field Fq is cyclic. In fact, the proof that we have given shows even more. It shows that if you take, as remarked earlier, you take any finite subgroup of the multiplicative group of any field, and that has to automatically be cyclic. All right, so let's look at polynomials. Let me begin with the definition. So let F be a field, a polynomial, Fx over F is irreducible if F has positive degree and whenever you can write F as GH for some polynomials G and H, either G or H is a constant polynomial. Okay, I suppose that you may have seen this definition before. So let's quickly compute the irreducible polynomials of degree 3 over F2. So for a polynomial of degree 3 to be irreducible, it should not have any root in the field. So, well, there should be an x cubed term, and 0 is not a root, so the constant term cannot be 0, that should be 1, 2. But 1 is a root of this polynomial precisely when it has an even number of non-zero coefficients. So for 1 not to be a root, you need an odd number of non-zero coefficients. So the only such polynomials are these two. Okay, so these are the irreducible polynomials over F2. From the point of view of cryptography, certain irreducible polynomials will be particularly important. They are what are called primitive polynomials. So let me come to a definition of primitive. But before that, let's begin with the following proposition. So let f in fqx be a polynomial of positive degree with f of 0 not equal to 0. Then there exists a positive integer e not exceeding q to the n minus 1 such that fx divides x to the e minus 1. So let me begin with a proof of this. So we're assuming that the degree is positive and that 0 is not a root of f. So consider the following polynomials. So consider the remainder when each of the polynomials so look at all powers of x up to x to the q to the m minus 1. So consider the remainder when each of these polynomials is divided by f. The idea is to use the pigeonhole principle here. So these polynomials, none of them can leave a 0 remainder because f does not divide 1 and it doesn't divide the others because 0 is not a root. So all the remainders must be non-zero. But the maximum possible, the total number of non-zero remainders you can have modulo f, since its degree is m, is simply q to the m minus 1. Okay, so what the pigeonhole principle says is that there must be two of these that leave the same remainder, since they can't all be distinct and non-zero. Then there exist, this is of course by the pigeonhole principle, integers are distinct integers r and s such that f divides x to the s minus x to the r. Well, them leaving the same remainder would mean that f divides their difference. And from this it would follow that since f is co-prime to x, it automatically follows that fx divides x to the s minus r minus 1. Okay, and since s minus r is at most q to the m minus 1,
चैंग ने फिर से ज्वाइन कर लिया यार.
Yeah. All right.
ये मीटिंग दोबारा ज्वाइन करना उसमें मैडम
when you have
जम के देख रही है हमारे मैडम.
could I request participants to please mute themselves? Okay, thank you. All right, so if you're given a polynomial of positive degree with f of 0 non-zero, then f divides x to the e minus 1 for some e. So let's use this to make a definition. So based on this, we make the following definition. So let fx be a non-zero polynomial over fq. If f of 0 is non-zero, the smallest positive integer e such that fx divides x to the e minus 1 is called the order of f. Okay, and we'll denote this by odd f. And if f of 0 is 0, then we write fx is some power of r times gx. Okay, we could do this uniquely provided that g of 0 is non-zero. So write fx is x to the r gx with g of 0 non-zero and define order of f to be the order of g. Order of g is defined because we assume that g of 0 is non-zero. Okay, so for instance, if you take a non-zero scalar, then its order is simply 1 because it divides x minus 1. On the other hand, if we take a polynomial of this form, x minus a, then what is its order going to be? Well, it's simply going to be, when does x to the a divide x to the e minus 1? Precisely when the a to the e is 1. So basically this is going to boil down to the order of a in FQ, provided that we assume that a is non-zero. Okay, and this observation of the order of f corresponding to the order of a root can actually be generalized further. So we have the following theorem. So let f in FQX be an irreducible polynomial of degree m, and suppose that f of 0 is non-zero. Then the order of f is equal to the order of any root of f in the multiplicative group FQM star. Okay, so if it's an irreducible polynomial of degree n, then the root lies in FQM. And we need to look at, since f of 0 is non-zero, that root is non-zero, and we can talk about the order of the root in the corresponding multiplicative group. Okay, so let's quickly sketch a proof of that. So proof. Okay, so since f is irreducible of degree m, the root alpha will generate an extension of degree n, and that should be FQN. Now, if alpha is a root of f, then the other roots of f are, or rather let me say, then all the roots of f are basically alpha to the q, and so on up to alpha to the q to the m minus 1. Okay, so maybe quickly try to recall why this is true. So first of all, if f of alpha is 0, if alpha is a root of f and f has coefficients in fq, then f of alpha is 0 simply by taking qth powers. This implies that f of alpha to the q is 0. And so all these are clearly roots of f. Alpha is a root, alpha to the q is root, and so on. But I claim that these are all distinct too, and for that we'll need to use the fact that f is irreducible. So why are they distinct? Well, if you allow alpha to the q to the I is alpha to the q to the j for I less than j. Of course, both I and j lying in the set, lying from alpha to the q to the 0. So lying between q to the 0 and q to the m minus 1. Okay, so rather between 0 and m minus 1. Then what we could do is raise this to the q to the m minus jth power. So this would imply but this is simply alpha. Okay, and this would be a contradiction because I plus m minus j is strictly less than m. And since alpha is a root of a polynomial of degree, irreducible polynomial of degree m, this cannot possibly happen. So these are all distinct and they are precisely the roots of this polynomial f. Now we need to show that the order of f is equal to the order of any root. For that we need to begin with the observation that all these roots have the same order. So each of these roots has the same order. Why is that true? Well, this is simply because q is co-prime to q to the m minus 1. It's because the GCD of q and q to the m minus 1 is 1. Okay, the order of alpha divides q to the m minus 1 and q is co-prime to that order. So all of these roots have the same order. And this simply implies that f is irreducible and alpha is a root of f. So up to a scalar multiple, f is simply the minimal polynomial of f over fq. Therefore, fx divides x to the e minus 1 if and only if alpha to the e minus 1 is 0. Okay, so in other words, the minimum e for which this happens is going to be the same. Therefore, the order of f equals the order of alpha. I hope that that's clear. Okay, so what we have as a corollary of this is that if f is irreducible, of degree m, then the order of f divides q to the n minus 1. One needs to be a little careful here because this root could potentially be 0. So let's rule that out. So if f is a times x, then the order of f is simply, so let's also assume that a is non-zero because okay, so f is ax and a is non-zero, then the order of f is simply the order of a. Sorry, it's not the order of a, it's simply the order of the constant polynomial a. There you might confuse that with the order of a in a group, but nevertheless you have any constant divides x minus 1, so the order of f is 1 and this divides q minus 1. Okay, so there is nothing to prove here. But for any other polynomial, we could use the result above. So if, right, so if f is not x, then f of 0 is not going to be 0. And the corollary follows. From the above here. Since the order of alpha divides q to the m minus 1 for any root alpha of f. This alpha is definitely non-zero and it lies in fq to the m star, so it must divide the order of the group. So we would be done in this case. All right, so let's look at an example. So for instance, let's consider the following polynomial. X squared minus x minus 1 over f3. Okay, so let's compute the order of this polynomial. So first check that f has no roots in f3. f0, f1, f2 are non-zero, so f is irreducible because it's of degree 2. F is irreducible. And suppose we take a root. So let alpha be a root of f. Well, what do we know about the order of f? We already know that the order of f divides q to the m minus 1, which is 8 in this case. So we could, a small computation shows that the order of alpha should be some divisor of 8, and we simply need to compute. So alpha squared is alpha plus 1. We successively square and here we can already say that the order of alpha must be 8. Therefore, the order of f is 8. Okay, here note that here we have simply used the fact that alpha squared is alpha plus 1. All right, so let's make a definition based on this. So a polynomial fx over fq of positive degree m is said to be primitive if, or let me rather say primitive over fq if it is the minimal polynomial over fq of a primitive element of fqm. Recall that primitive elements of fqm are those that generate the cyclic group. So based on our example above, we could say that, well, this alpha has order 8, so it generates all the non-zero elements in f9, which is f3 squared. So for instance, x squared minus x minus 1 is primitive. So first of all, from this definition, polynomials, so they're going to be monic. And further, since we chose f of 0 cannot be 0, so the polynomial x is also ruled out. And further, they should be irreducible polynomials. So primitive polynomials, being minimal polynomials, are irreducible, and you can find them among the irreducible polynomials. So maybe at this point, the reason that primitive polynomials are important in cryptography is that you could use them to design linear feedback shift registers of high period and so on. And that's probably something that you will see later on in this workshop. So maybe let me end this part with a question. The question is, how many primitive polynomials of degree m are there in FQX? Okay, so how many primitive polynomials are there? Well, to count primitive polynomials, it suffices, since they are the minimal polynomials of generators, it suffices to count generators of this multiplicative group, FQ to the m star. And that being a cyclic group of order q to the m minus 1, there are precisely 5 of q to the m minus 1 generators. But each of these primitive polynomials of degree m precisely corresponds to m generators. So one would need to divide out by m. Okay, so it's pi of q to the m minus 1 upon m, where phi is the Euler-Tauschent function. In fact, one can show that that primitive polynomials are characterized by this fact that their order is the maximum possible. In other words, if you take a monic polynomial with f of 0 non-zero, then it is of degree m, then it's primitive if and only if its order is the maximum possible, which is q to the m minus 1. This is a fact that we will not prove, but nevertheless, it's a useful characterization of primitive polynomials. So let's now look at, so let's do some counting. So what I'm going to do next is to look at a formula for the number of irreducible polynomials of a given degree over f cubed. So for that, the following theorem will come in useful. So for each positive integer n, the product of all monic irreducible polynomials over f cubed whose degrees divide n equals x to the q to the n minus x. All right, so let me quickly sketch a proof of this. Well, we already know that if you look at this polynomial, then its roots are precisely the elements of fq to the n. And this factors into linear factors. Okay, so if you write this as a product of polynomials or irreducible polynomials over f cubed, then the factors must be distinct. Okay, so the first observation is that the polynomial x to the q to the n minus x factors as a product of distinct irreducible polynomials over f cubed. And another way to see this would be to simply compute the formal derivative of x to the q to the n minus x. So recall that if a polynomial has a repeated root, if f has a repeated root, then if f has alpha as a repeated root, then alpha is also a root of f prime. Well, in this case, the derivative of this polynomial is simply minus 1, since q to the n is a multiple of the characteristic. So this cannot possibly have any repeated roots. So this factors as a product of distinct irreducible polynomials over fq. Moreover, if alpha is a root of some irreducible factor g of this polynomial, then alpha is an element of fq to the n. So in particular, the degree of this, since g is irreducible, its degree must be equal to the degree of this extension, fq to the alpha over fq. And that in turn must divide the degree of f q to the n over fq, which is n. Okay, so this proves that any reducible factor you have of that polynomial necessarily divides n. On the other hand, if you take any irreducible polynomial, so conversely, given any irreducible polynomial g of degree m that divides n, we have, so if you are given any irreducible polynomial like this, then if you look at a root alpha, then any root alpha of g satisfies fq alpha must be fqn. This is irreducible of degree n, and that is contained in fqn. Okay, so maybe one way to see this would be to directly see that these polynomials divide each other. So alpha lying in fqm okay, if m divides n, then x to the q to the n minus x divides x to the q to the n minus x. That follows from the fact that if k divides L, then x to the k minus 1 divides x to the L minus 1. Okay, so this would mean that alpha lies in fqn itself, which means that since it follows that gx will divides x to the q to the n minus x. Okay, I hope that is clear. So we showed that the irreducible polynomials whose degree dividing n are precisely those that appear in the factorization of x to the q to the n minus x. So as a corollary, we have the following. So if we look at the factorization of x to the q to the n minus x, then we could count degrees. So let nqd denote the number of monic irreducible polynomials of degree d over fq. Then q to the n is the sum over the divisors of n, d times NQD for each positive integer. Well, why is that true? Well, simply it follows from the previous theorem by comparing degrees. So you look at, so q to the n is simply the degree of x to the q to the n minus x. Whereas on the right hand side, we know that we have all polynomials of degree d appearing whenever d divides n. Well, corresponding to a given degree, corresponding to a given d, what is the total contribution to the degree on the right hand side? Well, there are NQD polynomials, each having degree d, so d times NQD is the total contribution, and that results in this expression. And this formula, this expression can be inverted to give an explicit formula for this NQN. So the idea is simply to use Mobius inversion. So let me quickly recall what that is. So Mobius inversion. If f and g are functions defined on the set of positive integers with Gn being the sum over the divisors, or sum of f taken over the divisors at the divisors of n, then f of n is the sum g of d times mu of n by d, again taken over the divisors of n. One could also write this. Well, maybe I should have defined this function mu. So let me quickly say what that is. So mu n, we define it for all positive integers in the following way. So mu of n is 1. If n equals 1, it's minus 1 to the r. If n is a product of r distinct primes, and 0 if n is divisible by the square of a prime. I guess I could just have said 0 otherwise. All right, so we could use Mobius inversion here. So let me just state that as a theorem. The number of monic reducible polynomials over fq of degree n equals nq of n is 1 by n times the sum over the divisors of n, q to the d, mu of n by d. Okay, so how do we prove this? Well, we simply start with the identity we had earlier. So q to the n is the sum over the divisors of n, d times nqd. And we apply Mobius inversion to this, and that will tell us that n times nqn, the sum over the divisors of n, q to the d times mu of n by d. Okay, and then we simply divide out by n. Okay, so maybe let's look at a quick example here. So let's try to compute. So let's say MQ18. Okay, so for instance, this must be the sum. So let's directly write that down. So Q to the D times mu of n by D. So I need to, so mu vanishes whenever the argument is not square free. So we only need to consider the square free divisors of 18, which would simply be 1, 2, 3, and 6. So this must be Q to the 18 times mu 1 plus Q to the 6 times mu 3 plus, well, we could take mu 6 as well, so QQ times mu 6. Okay, and that's simply mu 1 is 1 by definition, whereas mu 2 and mu 3 are minus 1. While mu 6 is simply 1. Okay, so there we have it. So maybe I would remark at this stage that this number MQD is, well, so it is always an integer, but there is an alternative interpretation in terms of, it can be shown that if you fix D, then this is strictly increasing as a function of Q. In other words, if you fix your degree, then as the field size increases, the number of irreducible polynomials also increases. And perhaps another thing one could do here is to say that, let me just make a remark that the expression for NQN can be used to show that, well, that for each positive degree, there exists irreducible polynomial of that degree. Okay, so to show that there exists an irreducible polynomial of degree D for each positive integer D. Why is that? Well, we could bound this NQN from below, so it's at least, so we have a Q to the N, but all the remaining terms we could give a lower bound by replacing the mu's by minus 1. So Q to the N minus 1, Q to the N minus 2, and so on up to Q. And this is simply Q to the N, Q to the N minus Q upon Q minus 1. Okay, we simply need to sum a geometric series here, and well, the Q to the N minus Q upon Q minus 1 is strictly less than Q to the N. So for sure, this is certainly positive, but we know that NQN is always an integer. So then it must be at least 1 since it is positive. Okay, so I guess that completes this. All right, so maybe since it probably doesn't make sense for me to make another definition since we are more or less out of time. So maybe I'll stop here for now. And if there are any questions, I would be happy to answer them.
Okay, at least I'm not able to see any question in the chat box. So if you have any question, you can unmute yourself and you can ask question directly.
Excuse me, sir.
Yes, Ridhima, please go ahead.
Yes, please go ahead.
Sir, for the definition of order of F, you said for C not equal to 0, order of C is 1.
The definition of order of F. So which page are you talking about?
I think second or third page it is.
It's on second page, I guess. Yeah, here.
Yeah, this one, sir. No, the previous
Yeah, this
one.
one,
Yes,
yeah.
sir. So in this example, you said that C is non-zero for C belonging to FQ. Order of C is 1.
That's right.
So here C is any constant in FQ, right? Any
That's
element
right.
of...
Okay, so I actually kind of mentioned this briefly. So you're not. So there is a chance for potential for confusion here because you could think of C, the order of C in the multiplicative group, but here I mean the order in the sense of this definition of order. So what is the smallest e such that C divides x to the e minus 1? That's what we need to think about. And here, if C is any non-zero constant, simply taking e equals 1 will do because C simply divides x minus 1, which is why its order is 1.
Okay. Okay, sir. Got it. Thank you so much.
Okay, you're welcome.
Yeah, is there any other question? You can unmute yourself and you can ask questions. Yeah, it seems there are no more questions. So let us thank the speaker for such a wonderful talk. Thank you, Samrit. And I think the next talk is at 5 o'clock Indian Standard Time by Professor Sudhir Ghorpade. And there is a half an hour break. So we'll meet again at 5 o'clock.
So I just want to remark that what Samrit did will be very basic and useful to lots of subsequent lectures, especially in cryptography. What Satas and Ventus Stanica, etc. will be doing. If Samrit allows, we can start with notes on the book page of the website. You can put the
sorry, I'm not able to hear you so well. Your voice seems...
Sir, your voice is not clear, sir.
Yeah, your voice is not clear for some reason.
Okay. Wait. Yeah. Can you hear me?
Yeah,
Hello?
now it's better.
Okay. I was just saying if somebody can share with us the PDF of this notes, we can put it up on the...
I would be happy to share these notes with you.
Yes. The basic material which lots of lectures will use.
Right, sure.
So we can also request all the speakers for their consent as quickly, as early as possible, because students are asking for recording and it will be good.
Yeah, but
during the workshop, they have some energy and motivation.
Okay, but right now I'm not promising the recording.
Yes, okay.
And slides, yeah, maybe with notes.
Okay, sir.
Thank you, and see you again.
So see you at 5 o'clock Indian Standard Time.
Hello.
Hello, good afternoon, sir.
Good afternoon.
So we start in 3 minutes.
Okay. Let me just try to share the thing.
Can you put your camera on, sir, for a while?
Yeah, just give me a minute. Huh?
Yes, your voice is little low, weak.
Okay, can you see this?
Yes.
Yeah. Yes.
Okay. Can you hear me?
Yes, sir.
Yes, sir.
Okay, then we
Yes. So we have still 1 minute.
Yeah. I'll just try to do a full screen. It blanks out for a minute. And then it should come on.
Yes, it is.
Okay.
Yeah,
So
it is visible.
And are you able to see me?
Yeah, yeah.
Okay. Because since it is full screen on my machine, I don't see myself for others.
Yeah, but you are clearly visible as well as the slides are also visible.
Wonderful. So I will just ask one of you, maybe Sartaj or Arun, if there are any questions in the chat box that need urgent attention, you please tell me orally, and I'll try to address.
Sure.
Yeah. So Arun, you would like to start?
Yeah. So shall we start, sir?
Yeah, sure.
So before we start, just a few words of introduction to Professor new speaker. So it is a great honor to introduce the speaker of this hour, a very great and very popular teacher in mathematical community, Professor Sudhir Ghorpade. He is currently an institute chair professor in the Department of Mathematics at IIT Mumbai. His research interests includes algebraic geometry, combinatorics, coding theory, and commutative algebra, and is widely acknowledged for his fundamental contributions in these fields of mathematics. Besides, sorry, yes, sir.
Just make it short. You must mention my title. I think
Sorry, sir.
Just mention my title. I think we don't have to have a long introduction.
Okay. Okay, so I welcome Professor Sunil Ghorpade to continue.
Yeah, okay. All right. Thank you. Arun is extremely kind and generous. So I didn't want him to eat up some time of money.
Prashant Singh is laughing there.
And also I just want to make a correction here. So I was an institute chair professor. It is sort of, it has a limited term. So at the moment I am not. So,
okay.
But of course I'm still a professor in the Department of Mathematics at IIT Bombay. Anyway, it's not about me, but this is about, workshop and especially mine is sort of a first lecture on coding theory. Of course, the very basic background has been already discussed by Samrit, namely the notions of finite fields and polynomials over fields, etc. So I'm going to start and give you a very rapid review of some of the basic things in linear codes. In these two lectures, so today I will mostly talk about linear codes, and tomorrow I will talk about Reed-Miller codes, which is an important class of codes and of some interest to many of us here. Okay. So let's just get started. So typically, if you sort of open a book on coding theory, you will see a picture where you have a message which is encoded and sent across what is called a noisy channel. And basically, this is a subject which originated from the problem of transmitting information in a manner that is effective, in a manner in which you can detect or correct errors. Okay, so the goals of coding theory are somewhat opposite of cryptography in the sense, in cryptography you have some message, maybe your credit card number, and you want to make it cryptic so that nobody can figure it out. Whereas in coding theory, you're not so much worried about hacking, but sort of getting the data effectively. So for example, this could be data sent from a satellite which is hovering around Mars, and you don't want that data to get corrupted and so on. Or it could be a music that you hear on CD players, etc. All right. So what the subject sort of basic idea is that what you do is instead of sending the original message, you just add some redundancies. So message in this digital world could look like a long strings of zeros and ones. And you add a few extra zeros or few extra ones in a clever way, so that even if one of the ones becomes zero or zero becomes one, so errors are there, they can be detected and sometimes even corrected. Okay, that's a basic idea. So what is a message then? So for example, you just have a finite alphabet set. I'll denote it by capital Q. Most widely used example of alphabet set used in digital world is just a binary set 0, 1. And the message would then be a k tuple where k could be some several million. And what then encoding would mean that you sort of transform that k tuple to an even bigger n tuple. So you just have a map from qk to qn. And for this encoding to be anywhere close to reasonable, this map should send distinct k tuples to distinct n tuples. In other words, you want this map to be injective. So encoding is just an injective map from qk to qn. Okay, and the image of this map, whatever is sitting inside qn, this longer bit sequence, they are what are called code words, and together they constitute a code, or more specifically an error correcting code. And because this tuple has length n, we say it has length n. Okay, and most widely used classes of codes and interesting ones are where the q has an algebraic structure such as that of a finite field, and then of course the injective map from qk to qn, it's a map of finite dimensional vector space, and it's natural to want it to be a linear map. So when q is a finite field and the encoding map is linear, we say that the corresponding code is linear. Okay, so that's the sort of genesis in short without drawing any diagrams. And I just want to mention some basic references. These are two most basic books on coding theory, which I like to call the Old Testament and the New Testament. Pardon me if I don't seem like secular, but the first is a classic treatise of McWilliams and Sloan called The Theory of Error Correcting Code. So that's Florence J.C. McWilliams. who made fundamental contributions to this subject. So I kind of mentioned that because today is also International Women's Day. So greetings to those of you of the International Women's Day. She made, as I said, great contributions to coding theory and wrote this book with Neil Sloan, which is about 750 pages. So you have a lot of material there. And but then there is an even bigger book, which is a compilation of articles by various experts, and that's called the Handbook of Coding Theory. It's edited by Vera Plus and Huffman. I don't remember if Duarte is also there. Anyway, this is about 2,000 pages. So if you want to understand coding theory, maybe you read this 2,000 pages or 750 pages and you have a fairly good grasp. Unfortunately, I don't have that luxury in this lecture. I just have 1 hour and maybe a small finite number of slides to tell you several basics. So obviously, I won't be comprehensive. There are, of course, many other books. I just mentioned the authors here, Van Lint, Justesen and Hoholt, Ling and Zing, and Fassmann, Bladut and Nogin. So they wrote a book called Algebraic Geometric Codes, Basic Notions, way back in 2007. And recently, a sequel to that called Advanced Chapters has also come in, also called Algebraic Geometric Codes. And I myself wrote a brief set of notes for some lectures which took place in various places, and I call it Aspects of Coding Theory. It is of a much, much smaller size than the Old or the New Testament. Okay, so I have given a link here. You can also find it on my homepage. Okay, very good. And I will make these slides available. So now let's get started. I'm going to have sort of at least one slide on general codes. By that mean codes which are not necessarily linear. Definition is extremely simple. A query code, just a code of length n over a finite alphabet set q is a subset of q to the power n. It is just a set of n tuples of elements from this finite alphabet set. Extremely simple-minded definition. Whatever is the size of that subset, cardinality of C, we call the size of C. And if I take the logarithm of that to the base q, q is the size of the alphabet set, then that's called the dimension of C. On this q to the power n, the n tuples, there is a very simple-minded notion of distance. Namely, distance between two n tuples is simply the number of coordinates in which they differ. Okay, so there you are. And the minimum distance of a code, which is a very important parameter, is defined to be the minimum of the Hamming distance between any two code words, any two elements of C, which are distinct. So think of it as some huge n-dimensional subspace, but with kind of finite coordinate points on each axis. And what you kind of want to do is sort of pack a subset inside that in such a way that this minimum distance is large. I will explain you why is that. Okay, but then how large can it be? There is a very simple bound that it satisfies, and that's called singleton bound. In fact, if you sort of fix a minimum distance d, okay, this is one way of stating it, then the maximum possible size of a query code of length n and minimum distance d, which is typically denoted by a sub q n d, is at most q to the power n minus d plus 1. Okay, so if I denote by k the dimension of C, so remember dimension is log to the base q of size of C, then I'm sort of having that log to the base q size of C is less equal to this. So sorry, how shall I say? So this is, I'm saying that mod C is less than or equal to this. And if I take log on both sides, I will get k less than or equal to n minus d plus 1. Or put it another way, d less than or equal to n minus k plus 1. You can think of this as a bound on the dimension of a query code of given length and given minimum distance, or a bound on the minimum distance of code of length, given length and given dimension. Very good. How do you prove it? Proof is actually very easy. And let me just give a one-line proof. So here is a proof. Suppose D is the minimum distance of a code C. Just not necessarily linear, just a query code of length n. Okay. Now I look at the projection map. So C is sitting inside q to the power n. So I look at the projection on q to the power n minus d plus 1 on the last n minus d plus 1 coordinates. What is that? I just forget the first d minus 1 coordinates. I take x1 to xn and I map it to xd plus 1 xn. I claim that this must be injective. Okay, now if you have not seen this before, pause for a minute to think. Why is this injective? What does it mean to say it is injective? That means distinct points go to distinct points. So if I have x1 to xn and y1 to y, and if their images are same, then I claim that x equal to y. Okay, but see what happens if the images are same. That means the only coordinates where they potentially differ are the first d minus 1 coordinates. So if x were not equal to y, then the Hamming distance between them will be d minus 1 or less. But d is supposed to be the minimum distance. It's the minimum of distance between any two distinct coordinates. So if two x and y go to the same n minus d plus 1 tuples, because d is the minimum distance, I must have x equal to y. In other words, this map is injective. So if I have an injective map from C to this space, obviously the cardinality of C is going to be less than or equal to the cardinality of this. And so that gives me cardinality of C is less than or equal to q to the power n minus d plus 1. And because my C was an arbitrary query code of length n, I get this bound. Okay, so that's the proof. So wherever proofs are simple, I'll just try to also include the proof because otherwise lecture gets boring. All right, so let's continue. Now I'm going to restrict myself to linear codes. So what are linear codes? So that will be our main topic for most of this lecture. So now, of course, I take my alphabet set to be a finite field with q elements. Somebody talked about this. So naturally, the size will have to be a power of a prime. Otherwise, there is no finite field with that many elements. So what is a q-array linear code of length n? It's simply a subspace of the n-dimensional vector space fq to the n. Okay. Now, if I have a code word, if I have not even a code word, just an element of fq to the power n, say n tuple x equal to x1 to xn, I define two things. I define the support of x to be just the set of those positions in which I have a non-zero coordinate. And the weight or the Hamming weight of x is the cardinality of the support. So number of positions in which you have a non-zero coordinate. See, because now you're in a linear setting, the vector space fq to the power n or the field fq has a distinguished element called 0. Okay, so I can talk about this. So you notice that if the Hamming distance that I just talked about, distance between x and y will be the Hamming weight of x minus y. So if you keep in mind that, then you will see that the minimum distance is same as the minimum Hamming weight of non-zero code words. So d of c can also, in the case of linear code, be thought of as the minimum of the Hamming weight of c. C runs over elements of C not equal to 0. Very good. I'm just going to define a slightly more general notion because some of our other speakers will use it. I define the support not just of an element but of a subcode to be, subcode means just a subset of C which is a subspace, which is the set of those positions for which there exists an element in that subcode C with the non-zero coordinate in that position. Okay. So if D were a one-dimensional subspace generated by X, this is exactly same as the support of X. Okay. Very good. So, so I'm assuming that X not equal to 0. So, and the weight of the subcode is just the cardinality of the support. With that, I can generalize the notion of minimum distance as follows. There is something called generalized Hamming weight, also called higher weight, and that is defined as follows. The rth generalized Hamming weight of C is defined to be the minimum of the Hamming weights of r-dimensional subcodes of C. So minimum of Hamming weight of D, where D runs over r-dimensional subcodes. Okay. Obviously, C has dimension k, so this r cannot exceed k, and I'll usually take r between 1 and k. Very good. Maybe I should have added one more definition. Which is that a code is said to be non-degenerate if it is not contained in a coordinate hyperplane of fq to the n. That means it doesn't happen that, say, the third coordinate is always 0 or some ith coordinate is always 0. If you think about this, this is exactly equivalent to saying that the last generalized Hamming weight, dk of C, is equal to n. I give you a minute to think about that. Just get myself some water. So let us continue. By the way, if there are questions, you stop and ask me. The singleton bound, we just saw, what did that say? That said that D is less than or equal to n minus k plus 1. So the code is called MDS code if this singleton bound is made. If minimum distance is equal to length minus dimension plus 1, which is the maximum it can possibly be, okay, if n and k are fixed. So such a thing is called MDS codes. MDS is actually an acronym. It stands for maximum distance separable. But almost nobody says maximum distance separable. Everybody just calls it MDS codes. So I'll just stick to that terminology. Okay. If you open the book of McWilliams and Sloan, and there is a chapter on MDS code, and he calls it the most one of the most fascinating topics in coding theory. And if you see that, you will see a reason. So I just want to give you a simple exercise. My notes will also contain some exercises. So suppose I am fixed k and n, dimension and the length, k less equal n. Find a formula for the number of NKQ code. So by the way, did I define NKQ code? Yeah, here. NKQ code means a linear code of over FQ of length n and dimension k. So I will often shorten this by saying NKQ. Okay. Very good. So this is a simple doable exercise. Basically what it amounts to is finding the number of k-dimensional subspaces of FQ to the power n. That's what it is. Not difficult. Here is a problem. Problem is determine the number of NKQ MDS codes. All right, you might ask what is the difference between exercise and a problem. Exercise is a problem whose solution I know, and problem is a problem whose solution I do not know. So this is actually a sort of an open problem. Of course, there are many special cases are known, etc. So if you want to have fun about this, you can try it for small cases. For example, you can try to solve it when k equal to 1, which is a trivial case, and k equal to 2, which requires a little bit work, but manageable. Okay. So that means it's a counting problem, combinatorial problem. Number of those subspaces of dimension k of FQ to the power n, such that if I look at the minimum distance, then that is n minus k plus 1. You want to count such things. And how do you do that is an interesting question. So I just mentioned that because just with basic stuff, we can already get to a problem which is quite interesting and difficult. Okay. I want to introduce to you or recall for you the notions of generator and parity check matrices. So what is that? So let us suppose C is an NKQ code. So k-dimensional subspace of FQ to the power n. By the way, it's a standard convention in coding theory to think of elements of FQ to the power n as row vectors. I know that in courses in linear algebra, you often think of elements in Rn, etc. as column vectors. But here we will think of them as row vectors. So x in FQ to the power n, I will think of it as a row vector. If I want to write down the corresponding column vector, I will just put a capital T as a superscript. So x transpose will denote the corresponding column vector. So, what is a generator matrix? A generator matrix, of a code C is basically a k cross n matrix with entries in FQ. This is an obvious notation for k cross n matrices with entries in FQ. With the property that the rows of that k cross n matrix, those k rows, thought of as elements of FQ to the power n, form a basis of C. So any k cross n matrix with entries in FQ whose rows form a basis is called a generator matrix of C, for obvious reasons. And because I told you that dimension of C is k, it will follow that the rows are linearly independent, so the rank of G is full, which is k. And because they form a basis, so the rows are like multiplying the matrix on the left by the standard basis vector, and every element in FQ to the power k will be a linear combination of the standard basis vector. So you will see that if I look at u times g as u runs over FQ to the power k, what I get is precisely all possible linear combinations, FQ linear combinations of the rows of G. And because these rows form a basis, that will constitute C. So C is completely determined by G. On the other hand, if I'm given C, the generator matrix may not be unique. In fact, two generator matrices could give you the same code. When does that happen? Simple linear algebra tells you, suppose G and G tilde are generator matrices of the same code, then they will, they generate the same code if and only if one is obtained from another by left multiplication by a K cross K non-singular matrix. So say G tilde is equal to say E times G for some K cross K non-singular matrix E with entries in FQ. So E is in GLKFQ. So therefore, that means, in other words, G and G tilde are row equivalent. You learned that in linear algebra. So, and you know that any K cross N matrix is row equivalent to a unique matrix which is in the reduced row echelon form. So if I require my generator matrix to be in reduced row echelon form, then it is unique. Okay, otherwise it may not be unique. So reduced row echelon form, again, this rank is K, so there are no zeros of rows. I mean, there are no rows of zeros, but your pivots will kind of appear in certain K columns of this K cross N matrix. I don't know, J1, J2, Jk. If it so happens that the pivots appear in the first K columns, which means the generator matrix looks like identity matrix of size K and some other K cross N minus K matrix, then you say that it is in standard form. Okay, mind you, it's not necessary that every code has a generator matrix in standard form. Reduced row echelon form, yes, but standard form may or may not happen. Okay, now I introduce to you what is called a parity check matrix. This is another important matrix associated to a code. So it's of size N minus K cross N, and that's called a parity check matrix if the code is its null space. Okay, linear algebra teaches you that this N minus K cross N matrix will sort of give me a map from FQ to the N to FQ to the N minus K, the map which sends say a vector X to HX transpose, and the null space of that is just the set of those vectors X such that HX transpose is 0. If that happens to be the K-dimensional subspace C, then we call it this H to be parity check matrix. So obviously, if this happens, that means if your null space is of dimension K, because C was the NKQ code, that means the range of this map will have to have dimension N minus K, which means rank of H is N minus K. Okay, so parity check matrix is also a full rank. Okay, here's a little lemma that suppose you have a code whose generator matrix is in standard form, say I and identity size of K and A, then parity check matrix can be given by minus of A transpose. Notice that the size is right. A was K cross N minus K. So minus A transpose will be N minus K cross K. And you adjoin to that on the right identity matrix of size N minus K. So you do get N minus K cross N matrix. Okay. So that is parity check matrix. How do you see that? Again, a one-line proof. Just do this block multiplication, H times G transpose. Suppose H is this and G is this. Okay, then what will I get? I take sort of minus A transpose into identity and plus identity into A. So but this is this G is transposed. So minus A transpose plus A transpose, and that is 0, the 0 matrix. So what does that show? That shows that I say remember the G transpose. That means the columns of these are the rows of G. So this H kills every column of G transpose, or H kills every row of G transpose. But the rows form a basis. So if I take anything in C, then it is contained in this null space of H. On the other hand, as I already remarked, so right now I don't know that. What about the other inclusion? Well, you just observe that this particular H is rank N minus K. Why? Because I have identity matrix of size N minus K. So and this space, therefore the null space will have dimension K, and C also has dimension K, so they have to be equal. Two K-dimensional subspaces, one containing another, they have to be equal. Okay, so that's that's a proof of this. Okay, let's continue. I want to relate parity check matrices to minimum distance. Suppose I have a parity check matrix H of a NKQ code C, and I just take a positive integer t. And now if I have a code word X whose Hamming weight is t and whose support is exactly J1 to JT, that means in J1, J2, JT position, I have non-zero coordinate, everywhere else it is 0. Then it turns out that the columns of H indexed by those same coordinate positions, J1 to JT, are linearly dependent. Conversely, if some T columns of H are linearly dependent, but no proper subset of these columns is linearly dependent. That means anything smaller than T is linearly independent. So if I take T minus 1 columns or less, it's linearly independent. Then C will contain a code word of weight T. Okay. The lemma statement is much longer than its proof. So proof will be just one line. So here is a proof. Just observe that if I take some vector x equal to x1 to xn in fq to the power n, then x is in C if and only if hx transpose is 0. We observed that when H was the parity check matrix, it's null space. And what does it mean to say that hx transpose is 0? So if Hj denotes the columns of the matrix H, then it basically means that the linear combination of these columns Hj with coefficient, the coordinates of x, xj, summation xj, xj. This is just the understanding matrix multiplication. So as you can see, if I had that support where this, support of x where this, that means those t coordinates are non-zero, everything else is 0, then I have a non-trivial linear combination of those t columns to be 0. So that means they are linearly dependent. Conversely, if some t columns were linearly dependent, so some combination of t of these edges is 0, not all x non-zero, then you can show, but no proper subset of these columns is linearly independent, which will kind of force all the coefficients to be non-zero. So then you have to have that x, the coefficients, the scalars, will give you a code word of weight t. And because this combination is 0, this x is in C. Okay? So that's the proof of this. This lemma has a useful corollary that suppose I have a parity check matrix H of NKQ code C, and I take a non-negative integer d. Okay, so this is a characterization of the minimum distance. Then d is the minimum distance of C if and only if every set of d minus 1 columns of H is linearly independent and there exist d columns of H that are linearly dependent. You might like to compare this with the characterization of rank that you typically study. And you will notice that this is a little opposite. The linearly independent and dependent are switched. Anyway, so how do you prove this? Well, it just follows from the lemma. So what does it mean to say that d is the minimum distance? That means the Hamming weight of every code word is bigger than or equal to d, and there exists something in C whose Hamming weight is equal to d. So Hamming weight is, so now you just apply the last lemma. That means, for example, suppose d is the Hamming weight, then every set of d minus 1 columns has to be linearly independent. Why? Because if they were linearly dependent, those d minus 1 columns, then I would get a code word of Hamming weight d minus 1, which would be a contradiction to the minimality of d. And on the other hand, there exists a code word of Hamming weight d, and this will mean that some d columns are linearly dependent. There exist d columns which are linearly dependent. So that proves this. If any of you is thinking about that problem I asked you about MDS codes, then this lemma is a good hint for that. If you want to start thinking about it. Okay. That is a small cryptic remark I make. Very good. Let me turn to duality of codes, which is a very fundamental notion. So I have something like an inner product defined on the space fq to the power n. Of course, it's not really an inner product. What I have is a non-degenerate symmetric bilinear form. It's basically a notion of like dot product. So this scalar product, dot product, of x and y is just x1, y1 plus x2, y2 plus dot, 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 x and y. Okay. What you don't have is you don't have positive definiteness. It doesn't even make sense. I mean, what is positive in FQ and what is negative? Somebody didn't tell you that, and I'm sure nobody can really tell you that. So, I mean, these are notions which are in classical fields like real numbers or rational numbers. Okay. Very good. So once you have this notion of, once you have this bilinear form, the dual is easy to define. So if I'm given a code C, the dual of C is defined to be set of all vectors Y in the ambient n-dimensional vector space fq to the power n, whose dot product with x is 0 for every x in the code C. So those vectors whose dot product with every code word is 0 constitute the dual. It's easy to see that this is a linear subspace of fq to the power n. This follows from elementary properties because it's a bilinear form. Okay. It is also, it's a small exercise, but not at all difficult to show that the dimension of this linear subspace is precisely n minus k. Okay. So I would like you to think about this. This is an exercise every student of coding theory should be able to do. And another easy exercise is if I take the dual and take the dual again, then I will get C. You can already see one inequality, one inclusion from the definition, and then you can compare the dimension if you have done exercise part 1. Okay, another exercise for you is that a code is MDS if and only if its dual is MDS. You might like to think about this. Very good. As I was saying, the notion of positive definiteness does not make sense for the bilinear form that I defined. So it can happen that a NKQ code satisfies so it's not that C intersection C perp is 0. On the contrary, you could have C contained in C perp. Okay. And in fact, you could also have that C is equal to C perp. So in the first case, I'm sorry, some part is cut out. C is said to be self-orthogonal. Every element of C is in its dual. And in the second case, when C is equal to C perp, the code is said to be self-dual. Okay. Very good. So self-dual means C is contained in C perp. Self-dual means C is equal to C perp, and self-orthogonal means C is contained in C. This can happen. Nonetheless, dimension of C perp is complementary, is n minus k. Very good. I want to talk about the spectrum or the weight distribution and what is called the weight enumerator polynomial. Okay. So what is a spectrum or weight distribution of a code? Well, basically what you do is you have your code, everything is in the finite world. So you have a k-dimensional subspace of fq to the n. So different code words, different elements of C have different Hamming weights. And what are those Hamming weights possible? Well, the Hamming weight can be 0. This happens exactly when the code word is the 0 vector. Or it can be 1 or it can be 2. And because there are only n coordinates, the possibilities are 0, 1, 2 up to n. So what you do is you just count the number of code words of weight 0, number of code words of weight 1, weight 2, and so on. So number of code words of weight I, that's denoted by A sub I or A sub I of C, because this is for the code C. And these, if I sort of list them as a tuple, then that's called the weight distribution or the spectrum. So I mean, if you know this sequence, you know a whole lot about codes. And usually it's not easy to determine the spectrum. Okay. One compact way in which to write the spectrum is by encoding this AIs as the coefficients of a polynomial. And it's convenient to take a two-variable homogeneous polynomial. So what you do is you take AIC, x to the power n minus I, y to the power I. So this is A0, x to the power n, plus A1 x to the power n minus 1 y plus A2 x to the power n minus 2 y square, and so on. So that summation, that's a homogeneous polynomial of degree n. That's called the weight enumerator polynomial of C. Notice that another way to write it, because every code word has weight I for some I, is just you take x to the power n minus the weight of C and y to the power the Hamming weight of C as C runs over the code C. So because this C will partition into code words of weight 0, 1, 2, 3 up to n, if you observe that, then you will just get back this summation. So this is what is called the weight enumerator polynomial. Giving the weight enumerator polynomial is one and same thing as giving the spectrum. Okay. Now what I want to tell you, unfortunately I don't have time to give you a full proof, but I want to give you some idea, is that quite surprisingly, if I take a code C of linear code of dimension k, I have its dual C perp, which has dimension n minus k. Okay, so then I have the spectrum of C, I have the spectrum of C perp. There are n numbers in one basket. I have another n numbers corresponding to C perp. And there is a wonderful, beautiful relationship between the two. And this is given by what are called McWilliams identities. So I can state this, but I just want to motivate this a little bit. So let me try to explain a special case of McWilliams identity. Okay. All right. So let us suppose C is a linear code of length n dimension k. I will write the spectrum of C in short as AI, and the spectrum of C perp, I call it BI. Okay. So these are the number of code words of weight I. For C, that's AI, and similarly for C perp, that's BI. As I have already remarked, for weight 0, there is only one code word, no matter which linear code it is, namely the 0 vector. Okay, that's always there. So A0 is always 1 and B0 is always 1. And now look at this, look at the summation AI, I going from 0 to n. If I do that, what happens? So what is AI? AI is like the number of code words of weight I. So I can write this AI as in following Knuth as summation of 1 added to itself as many times as there are code words of weight I. But now I exercise my birthright as a mathematician, namely to interchange finite summations. And now I can sort of push this C in C outside. And I can, in fact, if you sort of think about this, this double summation will cover all possible code words in C because it will have a unique weight which can be number I between 0 and n. So this is really some 1 added to itself as many times as there are elements in the code C. So that's just the cardinality of C, which is q to the power k. Is that related to BI? Well, in a trivial way, yes, because B0 is 1, I can also write it as q to the power k B0. Okay. Now let me proceed a little bit more. Now think of this huge matrix, script M. What is this huge matrix? This is a matrix with q to the power k rows and n columns. And what are those rows? The rows are simply coordinates of the code words of C. So my C has a dimension k, so it has size q to the power k. So I write the first code word. It has n coordinates. That's the first one. Second one, nth one. Q to the kth one. So I'll get a matrix with q to the k rows and n columns, and that is sort of giving me the entire profile of the code C. Okay. So now look at a typical row. Suppose I have a code word of which has weight having weight j. Okay, what does that mean? That means out of those n coordinates, n minus j are 0 and j are non-zero. And how many such how many code words do I have weight j? Well, that's exactly a sub j. Aj is the number of code words of having weight j. So therefore this code word of weight j has n minus j zeros. Okay, and there are aj such code words. So the number of zeros in this huge matrix M will be, on the one hand, n minus j multiplied by a sub j. I hope that's clear. Okay? Because code word of weight j has n minus j zeros and there are aj such code words. And the j can be anything between 0 and n. Okay? So that's one way of counting number of zeros in this big matrix M. On the other hand, let us try to understand. Let us try to now not look at rows, but let me look at the columns. So look at the jth column. To begin with, I'm going to look at the possibility when jth column is the 0 vector. What does that mean? That means the jth coordinate of every x in C is 0. Okay. What does that mean? That means if I look at the jth standard basis vector Ej, okay, then that has inner product with x 0 for every x in C. In other words, Ej is in the dual of C. Okay, so this is the characterization. The jth column of M is the zero vector if and only if Ej is in the dual. Okay. So now look, Ej's and its non-zero scalar multiples, what are they? They are the ones which have 1 in one place and 0 elsewhere. And if I multiply it by non-zero scalar, these are precisely the elements of weight 1. Okay, having weight 1. So what does that mean? That means the number of J for which the jth column consists only of zeros, okay, will be what? Will be B1. B1 is what? The number of elements of Hamming weight 1 in the dual. And you have to divide by Q minus 1 because, scalar multiples are also included. So the jth column consists of only of zeros. That's, you think about this, is exactly B1 over Q minus 1. What about the remaining column? Suppose I have a column which is not full of zeros. Then I claim that every scalar there appears exactly Q to the power K times. Okay, in particular, 0 appears there exactly Q to the power K times. Why is that? Because think of the map X going to the jth coordinate, the projection map. This is a map from FQ to the N to FQ, and I'm thinking of that as a map from C to this. So to say that the jth coordinate is not full 0, which means it's a non-trivial map, and it's a non-zero map into a one-dimensional subspace. Therefore, kernel is K minus 1 dimensional. Remember, C had dimension K, and so therefore cardinality of the kernel is Q to the power K minus 1. Okay, so what did we have earlier? We counted the number of zeros in M by sort of counting by rows. Now that was summation n minus j aj. Now I count by columns. I can have some 0 columns. Everybody is 0. There are B1 over Q minus 1 of them, which will contribute B1 over Q minus 1 into Q to the power K. Or I will have, how shall I say this? I will have remaining columns. So forget this B1 over Q minus 1, subtract it from N. And in each of those columns, I have exactly 0 coming Q to the power K minus 1 times. So now you just add it up, just a simple manipulation. So you will find that you get B1 times Q to the K minus Q to the K minus 1 divided by Q minus 1. So Q minus 1 cancels, left leaves me with B1 Q to the K minus 1 plus N times Q to the K minus 1. And I can write it as pulling out Q to the power K minus 1 outside. I have a coefficient of B1 to be 1, and here the coefficient is N. So I can write it as summation N minus J, choose N minus 1 from Bj. Very small summation, J going from 0 to 1. So J equal to 0 is one term, N choose N minus 1, that is this, N Q to the K minus 1. And J equal to 1 is another, the coefficient is 1. Okay, very good. So that gives you, see, this is a nice relationship between the AJs and the BJs. And that's just a special case of this McWilliams identity. And there's a beautiful generalization of this, which I don't have time to prove. There are many proofs of this. You can find one proof in my notes. It says more generally, if I take summation, not just N minus J or N minus J choose 1, but N minus J choose new AJ, then that is equal to Q to the power K minus new summation N minus J choose N minus new BJ. Okay, so that's, so if I put new equal to 1, I get the identity I just proved. But in general, I have this identity. Okay? And this is really a preliminary form of McWilliams identity. So the traditional McWilliams identity is this, that Hamming weight of the weight enumerator polynomial of C perp is expressed as a weight enumerator polynomial of C when you substitute for x and y, x plus q minus y and x minus y, and you normalize by dividing by the size of C. So that's the relation. One special case is worthy of mention. When in the binary case, that means q equal to 2. So then this size of C will be 2 to the power k. So this left-hand side is the weight enumerator of C perp. Right-hand side will be 2 to the power minus k, but 2 minus 1 is just 1. So I have x plus y, x minus y, standard sort of transformation. But in the query case, this is the way the identity takes place. It's not difficult to prove this from the theorem that I have stated. So I'll just quickly outline a proof How much time do I have? How much? I have 15 minutes, Satraj? Arun?
Sir,
Yeah.
5:46. So,
yeah, okay, 14 minutes.
Yeah, 14 minutes.
Okay, thanks. So, okay, the way you do this is the following. You just call this, you just introduce a new variable z to be x minus y. Okay, that means write x is equal to y plus z. So if I write x is equal to y plus z, so this y and minus y will cancel. So I will get here so the left hand side will be WC perp of y plus z comma y, and right hand side will be z plus qy comma z. Okay, so I want to show these two things are equal. That's what I want to show. So you work on one of the sides. So look at the left hand side, y plus z comma y. What is this? By definition, this is bj, the first variable to the power n minus j, y to the power j. I use my binomial theorem to expand this. So this is summation n minus j, choose new, y to the power n minus j minus new, z to the power new, and this y to the power j, I have pulled it out here. Okay. Now I can add it, of course, here, so that we'll have y to the power n minus new. But again, I exercise my birthright. So I do that. I pull this in, then I get y to the n minus new, z to the new. I exercise my birthright to interchange these finite summations. So j going from 0 to n, new going from 0 to n minus j is equivalent to saying new going from 0 to n and j going from 0 to n minus new. See, new is less equal n minus j means j is less equal n minus new. And then I have these things, which this is the only thing which depends on j. And I have y to the n minus new, z to the new. Keeping in mind my previous identity, I'm just going to make a standard interchange. I just add from top to bottom, so to speak, then bottom to top. So in other words, change new to n minus new. If I did that, the summation will remain the same, but new becomes n minus new. And then this n minus new will become new, and new becomes n minus new. Okay, so this is an expression for the left hand side of WC perp. On the other hand, the right hand side, which was this W1 over cardinality of C WC of Z plus QYZ. What is this? By definition, 1 over Q to the power K, AJ, Z plus QY to the n minus J, Z to the J. Expand by binomial theorem, I will get n minus J, choose new, Z to the n minus J minus new. And then I have QY to the power new. So that is Q to the new, Y to the new. And then Z to the J outside. Exercise my birthright, interchange summation. I will have new going from 0 to n. And then I'm also interchanging, okay. And then I have 1 over Q to the K here, but I have Q to the new in the denominator. So I bring it, I adjust it, I will have 1 over Q to the K minus new. And what is left inside is summation J going from 0 to n minus new, n minus J choose new, A sub J. And then what is happening? Y to the power new, and this two combine to give me Z to the power n minus new. And now you look at this blue expression here and the blue expression here, and the previous theorem exactly said that the two blue expressions are equal. Okay, so that gives me the desired result. So from the previous theorem, you get the desired result. I will just mention this in passing. There is a way to write this result or the identity in the previous theorem in the language of what are called Krautchuk polynomials. These are interesting objects which satisfy certain orthogonality relations and so on. And you can find more information about them in the handbook. But I just mentioned to you that they come naturally in the setting of McWilliams identity. Okay, very good. I have not given any examples so far, so let me do some examples. So first I'm going to start with some simplest examples of codes. One of the simplest classes of codes is called simplex code, and it is closely related to what is called a Hamming code. All right, what is that? So let us fix a positive integer r, and let me take n to be this number, q to the power r minus 1 upon q minus 1. What is that numerator? Numerator is like all non-zero vectors in fq to the power r. And when I divide by q minus 1, these are all non-zero vectors in fq to the power r, modulo scalars. That means I regard two vectors as equivalent if they differ upon multiplication by a non-zero scalar. Okay. The set of equivalence classes, by the way, is called projective space of dimension r minus 1 and usually denoted like this. So for those of you who know what is a projective space, this is precisely the cardinality of pr minus 1 over fq. Okay. Now what do? I take a R cross N matrix. Okay, so now here N is this special quantity, with entries in FQ in such a way that any two columns are linearly independent. Basically, what I do is I take columns to be representative in FQ to the power R of distinct elements of PR minus 1. That means I take non-zero vector in FQ to the power R, but once I have taken one, I do not take any multiple of this, because otherwise two columns will be linearly dependent. So you will see that the maximum number of such non-zero vectors in FQ to the power R you can put so that two columns are linearly independent is exactly this number n. So this matrix is well defined, at least up to order of its columns. Okay, and notice that the rank of this is R. Why is that? Because I'm essentially up to a scalar multiple, I'm taking every R vector, every non-zero R vector. In particular, my standard basis vectors or their non-zero scalar multiples would be there somewhere, 1, 0, 0, 0, 1, 0, etc. So there are R linearly independent columns in this matrix, and since the number of rows is R, that shows that the rank is R. Okay. So now I define the Hamming code, HR. What is that? That is a code of length n and dimension n minus R. It is precisely the code with this HRQ as its parity check matrix. On the other hand, if I look at a code for which HRQ, this R cross N matrix, is its generator matrix, then that I'm denoting by script SRQ, and that's called the simplex code. Okay, so this is the NR code, this is the N minus R code. And as you can very easily see, this is, HRQ is generator matrix in one case, parity check matrix in another case. So the dual of HR is SR, or dual of SR is HR. So the simplex code is sometimes also called the dual Hamming code. Okay. I have an exercise for you. Find the minimum distance of the Hamming code and find the minimum distance of the simplex code. This is a eminently doable thing. And because I said simplex is simple, you can try even more. You can try to find the weight distribution of the simplex code and its weight enumerator polynomial. You will notice that the simplex code is an example of what is called a constant weight code. That means every non-zero code word actually has just the same Hamming weight. So the weight enumerator polynomial is not so difficult. Besides 0, there is just one non-zero entry in that polynomial. Very good. I'm going to talk about Reed-Solomon codes now. This is another important example of code, and you will see much more about this in the next lecture by Peter Beelen. So what are Reed-Solomon codes? Well, here they are. Let us suppose n and k are positive integers, k less equal n, and I fix a prime power q which is big enough. So q bigger than or equal to n. Okay, so this is a code which kind of makes sense when my alphabet size, my finite field size is pretty large. Now, because q is bigger than or equal to n, in FQ I can certainly find n distinct elements. I just pick some arbitrary n distinct elements, a1 to n. And then what I do is the following. I take a polynomial in one variable whose degree is strictly less than k. Okay, that means degree is less than or equal to k minus 1. And I evaluate that polynomial at each of these fixed n points. I'll get a scalar. So I'll get an n tuple of scalars. I collect all these n tuple of scalars as f runs over all polynomials of degree strictly less than k. And you can easily see that that will be a linear subspace of f to the power n. And that's called, and therefore, a code of length n and dimension k. Okay, why dimension k? Because you see the evaluation map which sort of sends f to this c sub f is injective. Why? Because degree is less than or equal to k minus 1. In particular, it is strictly less than n. So if you have a polynomial of degree less equal k minus 1 and it vanishes at more points than its degree, it has to be the zero polynomial. So in other words, the dimension of this will be the same as the dimension of the vector space of polynomials of degree less equal k minus 1. And we all know that that dimension is k. 1 x square x to the k minus 1 is a basis. Okay. What about the minimum distance? Well, such a polynomial of degree less equal k minus 1 will have at most k minus 1 roots. Okay. So that means there are at least n minus k plus 1 non-zero entries. Okay. And you can, because my q is large enough, I can certainly find a polynomial of degree k minus 1 with exactly k minus 1 roots. So if I take that polynomial, for example, just product minus ai, I goes from 1 to k minus 1, then that will show that the minimum distance or the Hamming weight of any non-zero code word is at least as big as n minus k plus 1, and there exists a code word of this Hamming weight. So in other words, the minimum distance is n minus k plus 1. Notice that this is meeting the singleton bound. So in other words, this Reed-Solomon code is a MDS code. In tomorrow's lecture, I'll discuss another important example called generalized Reed-Miller codes. And let's see how much time I have. Oh, maybe only 3 minutes. Okay, so I want to quickly just also mention one more class of codes called cyclic codes. So a linear code is said to be cyclic if whenever a code word is there, I have this time denoted C0, C1, Cn minus 1 for a reason, you permute them cyclically. So you push Cn minus 1 to the first position and push forward others, then that is in C. And of course, you can keep doing that. So cyclic, it is closed under cyclic permutations. This is naturally related to algebra, because if I now denote by the ring of polynomials in one variable by this, and I quotient it out by the ideal generated by x to the power n minus 1, and I denote the image of capital X in this quotient ring by little x, then I get a ring for which 1x, x square, x to the power n minus 1 is a basis. Okay, and so I can now map an element of fq to the power n to this space by sending an n tuple to the polynomial c0 plus, sorry, this is a typo, c1x plus cn minus 1 x to the power n minus 1. So it's very easy to see that that's an fq linear isomorphism, and it maps nkq codes to fq linear subspaces of this space Rn. Okay, so now what does cyclic correspond to? You will see that cyclic shifts correspond to multiplication by x, x square, etc. So if you think about it, it's easy to see that a C is cyclic code if and only if this image of C inside this Rn is an ideal. It's not just a subspace, but an ideal of this. Okay, I have just 2 exercises for you. Exercise number 1, which is tells you that if I have, see, because you know how the ideals of this Rn look like. They basically look like ideals of a polynomial ring which contain this ideal. And the polynomial ring, that's a PID. So they are generated by a unique polynomial, and because they contain the ideal generated by x to the power n, this has to divide x to the power n. So every ideal has a unique monic sort of generator. So there is a unique monic polynomial gx which divides x to the power n minus 1, so that g of little x generates I, and that's called the generator polynomial. And this exercise, I will not read it out. It tells you that suppose this generator polynomial has degree n minus k, then the code has dimension k. Or conversely, if you know that the code has dimension k, the generator polynomial has to have degree n minus k. And it tells you how you can write down the generator matrix of C from the generator polynomial. And just one last slide, which tells you what are the parity checkmate polynomials of cyclic codes. I'm just going to leave it here, and I will stop and ask for questions. I will upload slides, so let me just come back to the video mode. Let's see. Okay.
So if there are questions from audience, we can ask.
Yeah. Any questions, comments are most welcome.
So, when you said that that you are not able to find standard matrices for all generator matrices, did you assume that column swaps are not allowed? I mean,
so, I was hoping to say it in this lecture. I'll say something about automorphisms of codes. So, yeah, column swap will generally give you a different type of different code. Okay, because remember, 2 matrices give you the same code if and only if they're row equivalent. Okay, So if you sort of swap, if you make elementary column operations, including permutations of columns, that will alter your row space. You can think about that. Okay. So, but however, what is true is that your code will be equivalent to or another code which has a generator matrix in standard form. So I have not discussed the notion of equivalence, which I was planning to, but then there are so many things I can do in 1 hour. I will try to say this, and then you will see. So it is not necessarily true that every linear code has a generator matrix in standard form. But every linear code is equivalent to a linear code which has a generator matrix in standard form. So up to, if you are willing to sort of take this notion of equivalence, which I have not defined, then standard form is good enough. But there are some problems where you don't want to that equivalence class is too coarse. Okay, there is a question in the chat box saying, why do we need quantum codes? What thing these linear codes do not have, so we need quantum codes? Well, I'm not an expert on quantum codes, and I'm not. Maybe some of the you should ask this question to Annalena or Frederick, who will be lecturing later in the course. They might be able to tell you. I don't pretend to know the answer. Any other question?
So I think there is no more questions, sir.
Okay. So by the way, I see in the audience, I think we can stop the recording. We can do.
Okay.
Chat perhaps. Yeah, I mean there are many experts in the audience. I see Michelle O'Rourke, Johnson, and Prashant and Peter Dillon. So I apologize because this may have been too elementary for you, but it was meant to sort of prepare a ground for students in the workshop. All right.
Yes, sir. Okay. Thank you very much, sir.
So now we can take a break.
Have a break again.
Then the next.
There is one more question in the chat box. So there is a question by Ritu Arora. So
you some open problems. Well, I already did find the number of NKQ MDS codes. That's a nice open problem. You know it for k equal to 2. You know it for k equal to 3, n less than or equal to 9. Beyond that, and these are already extremely complicated formulas. And beyond that, you don't have a good formula. However, in an old paper, Jill Lesho and I gave some explicit upper bounds and lower bounds for this number and an asymptotic formula. Recently, there has been a further improvement on that asymptotic formula, I think by Krishna Kaipa. So you can follow this, or you can just write to me if you're interested in that problem. Maybe tomorrow I might mention some more open problems if you're interested. In any case, this is just the first week of workshop. As it progresses, other speakers will also mention open problems. I just want to set some common ground and quickly review some basics. That was the purpose of my talk. Any other questions?
No, sir. There is no question. No.
Okay. All right. Thank you very much.
Okay. Thank you, sir. And we have a short break now.
Yeah.
So we meet at
6:30 Indian time.
Yeah.
About 26 minutes from now.
Yes. Okay. Okay. Thank you, sir.
Hi, Peter.
Hi. Can you hear me?
Yes, I can hear you. I can see you.
That's good.
Virtually we get to meet.
Dag Peter.
Hi.
Hello, Sudhir.
Hi.
So this making your screen visible is just the present now button, I suppose.
Yes, you're present now, and then probably you can choose the entire screen. Or I don't know if you're connecting a tab or something. Or
no, I simply want to show some.
Beamer slides.
Yeah. So let me just quickly try to see how it works.
We have 3 minutes.
Yeah. So does anything happen?
Not yet.
Okay. Okay. So now you should be able to see something, right?
No, but yeah. I think now something is happening. Yes.
Okay, so you should be able to see a picture of a whiteboard.
Yes.
Okay.
Beautiful. Okay. So this was a busy day for you.
Excuse me?
It was a busy day for you also today?
Yes.
Good. I see so it's still afternoon now in Europe?
Yeah, it's 2 o'clock. Okay. So that's...
Yeah, that's the thing. It's a little dangerous to make a generic greeting like good morning or good afternoon, because it could be different for people.
So only greetings.
Yeah, greetings, welcome. Okay, so shall we start, Arun, or 1 minute? Anyway.
Yeah, we can start, sir.
So, all right. So, friends, it's a great pleasure to have Professor Peter Billen, join us by this magic of Google Meet and so on. He's a distinguished researcher and a very nice speaker, as you will find out. Peter is a professor with special responsibilities at the Technical University of Denmark. Is that there is such a thing? And he's the head of the algebra group there. Until recently, he was also the head of mathematics section at the DTU, which is the Technical University of Denmark, located in a suburb of Copenhagen. Peter, I think, did his PhD in Eindhoven with Pelikan and Vandenberg and so on, and he has worked with many good people. He did a postdoc with Henning Stichteroth at Essen before he moved to DTU in Denmark. And he's an expert on many topics. He's a brilliant researcher. And today he will tell us about decoding of Reed-Solomon codes. I did not touch upon decoding at all in my lectures, and I'm glad that Peter would be doing that. So today and Thursday. So please, Peter.
Okay, thank you. So please, one of the organizers, let me know if something goes wrong with either the screen sharing or the switching from one picture to the next. So thank you for your kind words. You have a way of putting pressure on me, of course, by claiming I'm the speaker. So I'll do my best, of course. The organizers were increasingly generous with the amount of time they gave the speakers. So I actually decided to use my first lecture to introduce and prove some fundamental properties of Reed-Solomon codes, and to address most, if not all, of the decoding in the next lecture, on my second lecture. So if you already know the basics of Reed-Solomon codes, then feel free to let your thoughts wander, or even physically do something else. So that would be completely fine. So what I want to do is simply to introduce the Reed-Solomon codes and prove some of their properties. Of course, the third speaker, Sudhir, already told you a little bit about it. So there's going to be some repetition. So, okay, so now the most exciting part of my talk, seeing if the screen sharing actually works. So let me try to repeat the procedure we just tried. Okay. There seems to be some time delay. All right. So is anything actually being shared now?
Not yet, but we can let you know.
Yeah. Okay. Okay, so it seems I have to allow the browser. Yes. So I'm getting the message I have shared my screen.
Okay.
Now let's see if you agree.
Okay. Yeah, it's coming.
It's coming. Okay, good.
It takes a minute for it to come from Denmark to India, maybe. So.
Yeah, sure. I mean, as you say, it's quite a miracle one can arrange these things on such short notice nowadays. So, okay, so so you can see the picture of the whiteboard now, correct? Is that true? Can you see the picture?
Yes. Yes. Can somehow enlarge it? Yeah.
Yeah, sure. Okay, so so as the previous speaker already briefly mentioned, there are something called the Reed-Solomon codes, which is very simple once you have seen it to define, because all you need is a finite field. You pick any distinct elements of that finite field of your choice, and this gives rise to an evaluation map from the space of all polynomials to the vector space fq to the n by mapping a polynomial to each multi-point evaluation in these n distinct values. And this is a nice linear map, and if we restrict the domain of this evaluation map to polynomials up to a certain degree, then the image is called a Reed-Solomon code. So if we want this evaluation map to be injective, we had better restrict the degree to at most n-1, because if we allow degree n, we are gonna get an evaluation map with a non-trivial kernel, simply because the polynomial having all these n values from fq as a root would be in that kernel. But as long as the degree of the polynomials we evaluate is strictly less than n, we have an injective evaluation. And if we pick any k less than or equal to n, and we restrict the domain of the evaluation map to polynomials of degree strictly less than k, then the image is called a Reed-Solomon code. And somewhat ad hoc notation here, rs n, k of the vector x consisting of all the evaluation values. So that is very briefly what a Reed-Solomon code is. And I would just like to take a small moment to link this to some of the things that were mentioned by the previous speakers. So if you remember, then the second speaker today, Samrit Ram, he reminded everybody that a finite field with q elements is very special. If we look at the multiplicative group of it, so if we remove the zero element, we actually get a cyclic group. And this means that if we pick x1 up to xn to be successive powers of a generator of this multiplicative group, so if we pick powers over primitive elements, then we get a code of length q minus 1. And because of the cyclic nature of this multiplicative group, the resulting codes, the resulting Reed-Solomon code, will also be a cyclic code. So what a cyclic code was briefly mentioned in the previous talk. So these cyclic codes, these cyclic Reed-Solomon codes are sometimes called classical Reed-Solomon codes because these were considered a lot in the beginning of the history of these. So there's a link with cyclic codes through the cyclic structure of the multiplicative group of a finite field. And to link it also to what was mentioned in the first talk, if we have a Reed-Solomon code, then by nature it is defined over the finite field Fq. Well, if Q would be a prime power, let's say a power of the prime 2, then what you can do is you can pick your Reed-Solomon code and look at all the binary code word it contains. So in other words, we could look at the intersection of such a Reed-Solomon code with the vector space F2 to the n, in case Q is a power of 2. And if you do that, you get something that is called a BCH code. And we were reminded that the B stands for, if I pronounce it correctly, Raj Bose, which is a well-known scientist. But okay, the C and the H, they came from Ray Chaudhuri, and the H from Hockingham, just to have the whole acronym explained there. So BCH codes are very related with Reed-Solomon codes, and essentially, apart from these details in setup, you intersect FQ to the n with F2 to the n. And the intersection with the Reed-Solomon codes gives you then a binary code. So in particular, what I'm going to say later about the decoding of Reed-Solomon codes applies immediately to the decoding of BCH codes as well. Okay, I just wanted to make that link with what the previous speakers have been saying. So, okay, so we want to talk about the basic properties of a Reed-Solomon code, and it was briefly mentioned that the dimension of a Reed-Solomon code is indeed k, which is the reason to choose that symbol in the first place. And the reason is that the evaluation map is injective as long as the degree of the polynomial space, the polynomials does not exceed n minus 1. And since that is the case here, and the vector space of polynomials up to degree strictly less than k has dimension k, also the image is k-dimensional. So there's not so much we have to worry about there. So this is a very nice property that holds in this particular setting of Reed-Solomon codes. You're going to see other codes that are somewhat similar to Reed-Solomon codes in the sense that you evaluate algebraic functions, maybe polynomials in several variables, or you could also look at algebraic functions on an algebraic curve, but I don't think that is going to be a topic of this workshop. But you could do that as well, and then it is a bit more painful to figure out on which subspaces your evaluation map is going to be injective. So theoretically, it's not so hard, but in practice, you can get into combinatorial problems to figure out what the dimension is. But for Reed-Solomon codes, this is very easy. Okay, so let me see if I can easily go to the next picture. So if someone could confirm that now indeed you're looking at the different picture.
Yeah, yes.
Yeah? Okay, very good. So let's see if I can increase it slightly more. Yeah, good. So, okay, so what about the really basic parameters? The third one that's always mentioned in any math text about codes is the minimum distance. So it has been defined already, so I won't repeat that definition, but what has not been said out loud yet is what does this have to do with decoding? So the minimum distance is a measure for how many errors a code can correct. So what is going on is that we should imagine a scenario where a code word is being sent and the receiver receives still n coordinates, but some of the coordinates may have changed. But typically you model this behavior, this channel as it is called, in a very simple way. You say that the probability that one symbol changes has a certain value p, and the crossover probability is something. Typically it's very small, but it may happen that some of the coordinates have changed. But in this model, we don't assume you get problems with insertion or deletion of coordinates. That is a very different problem. So we just have a code word with n coordinates, each from the finite field with q elements. Some of them may change during transmission, others may not. You don't know in advance. Now this Hamming distance, this Hamming measure, this exactly tells you how many coordinates change. So what I mean to say is that if you subtract the received word and the sent code word from each other, then we get an error vector, as it is called, and you get non-zero coordinates exactly where the errors have occurred, and you get 0 coordinates where no errors have occurred. So the Hamming weight of this r minus c, r the received vector, c the sent code word, tells you exactly how many errors have occurred. This is why this Hamming distance works so well in this setting. And it's really a proper metric, so it satisfies nice things like triangle inequality. And in particular, it means we can think of the received word as having a certain distance from the sent code word C. Now, the minimum distance tells you what if you have two distinct code words, then they are at least distance d apart. So now if we bring in the received word in this picture, then we have a code word C, then we have the received word R at a distance, depending on the number of errors that has occurred, and then any other code word lies at least D away from the sent code word. So this means that as long as the number of errors is strictly less than half the minimum distance, the sent code word is still the unique closest code word to the received word. So this minimum distance tells you that if strictly less than d half errors have occurred, then at least in theory, it should be possible to uniquely recover the sent code word. So how to do that is a different matter, because it is not an easy problem in general. So the decoding is strongly related with the minimum distance, because it tells you kind of what to aim for, at least if we are interested in unique decoding. Okay, so for Reed-Solomon codes, we actually know the minimum distance, and it actually meets the singleton bound that the third speaker mentioned today. So what is the singleton bound? It says that the minimum distance of any linear code with parameters n and k and d will satisfy that d is at most n minus k plus 1. And Reed-Solomon codes actually attain the singleton bound. So Reed-Solomon codes are MDS codes. So how do you prove this? It was briefly mentioned. So what you do is, you simply have to realize what it means to be a code word in a Reed-Solomon code of very low Hamming weight. So if we pick any non-zero code word, then it comes from a non-zero polynomial. And that polynomial is assumed to have degree at most k minus 1. Well, then it can have at most k minus 1 roots, because we are working over fields. And that means that the minimum distance is going to be at least n minus the degree of the polynomial, which then in turn is going to be n minus k plus 1 at least. So that means that any non-zero code word has Hamming weight at least n minus k plus 1. So then we can conclude by the singleton bound, this gives you the other inequality, the reverse one, so equality must hold. We don't really need the singleton bound to prove this. It's very simple to create a code word of the right of this minimum weight by just picking a polynomial that has k minus 1 of these evaluation values as roots. But anyway, so that is not so important here, but we do know what the minimum distance is exactly. Okay, so then if you want to understand the code a bit better, it's always nice to be able to say something about the generator matrix and also about the parity check matrix of such a code. So, well, what is a generator matrix again? There are different ways of looking at this. So the way that was explained is that what we have to do is you find the basis of your code, you put these as rows in a matrix, and that is a possible generator matrix. So since there are many possible bases of a vector space in general, you also have many possible generator matrices. So you can pick the one you like best. One that is kind of very natural from the setup of this description I chose here is to pick a basis of your polynomial space, evaluate these. Since we had an injective evaluation map, the images are going to be linearly independent, and this is exactly a basis of your code. So if you do that, you pick the one polynomial, the polynomial x squared up to x to the k minus 1, evaluate these in all the evaluation points, and you get a van der Monde-like matrix. I mean, the van der Monde matrix is typically a square matrix. So if you would want a full one, we would have to truncate it or either add higher powers of it. But this is certainly a part of a van der Monde matrix. And so this is a possible generator matrix, and the one that you see often in the literature. However, it is not always the best one, so to say. What is quite convenient is to have a generator matrix that is in a slightly different form. So I think it was called by the previous speaker in standard form of a generator matrix. A term I use myself quite often is a systematic form of a generator matrix. So what is that? So a systematic form of a generator matrix would be where you start with an identity matrix and then some other things. The identity matrix, I think one of the questions zoomed in on this, does not necessarily have to be contained in the first k columns, but it could also be distributed over the matrix, so to say. But anyway, that's a minor detail. And for Reed-Solomon codes, as we will see, you can always put the identity matrix in the first k columns anyway. Yeah, so the only thing you really need to understand to create such a generator matrix is finite field arithmetic. If you know how to construct a finite field, you can work all these things out. And actually, these pictures were taken from a lecture I gave to students. So there I always add a small example just to make sure that people remember that a finite field with 4 elements is not the same thing as set modulo 4. But I'm sure that the audience here are all full aware of this. So let me skip this example as such and go over to the next picture. Okay. Yeah, so a systematic generator matrix. And as I said, what we're going to do is develop a little bit of theory so that we can construct this. And I'm going to place the identity matrix in the first k columns. Now, actually, why can you do this? So I'm claiming that if you pick any k columns of the generator matrix of an MDS code, so in particular of a Reed-Solomon code, then these k columns are going to be linearly independent. And that really means that you can create the identity matrix by elementary row operations in those k columns. And the reason is simple. If you would have a generator matrix and k columns of these would be linearly dependent, then it means that also the rows are going to be linearly dependent. And in those k coordinates, that is, And then you can perform a linear combination, a non-trivial linear combination of the rows, and create zeros in those k positions. But then you would get a code word that has Hamming weight at most n minus k. And since we had an MDS code, that's not possible. So you can pick any k coordinates you want, so in particular the first k ones. So we should be able to find a standard form or a systematic form of a generator matrix for a Reed-Solomon code as well. So let us try to do this. And what we're going to need is just a tiny bit of theory about interpolation polynomials. And what it is all about is that if we have polynomials up to a degree but not including m, and we evaluate this in m values, then we get a bijective evaluation map. So I've on purpose now not used the letter n here, but an m. And here the degree of the polynomials is up to and including m minus 1. So this m now matches the other one. So why is this? Well, it's really the same argument as before. A polynomial of degree m minus 1 or less cannot have these m evaluation values as roots simultaneously. So it's going to be an injective map. But now since the dimensions on the left and the right hand side are m, this must be actually a bijective linear map. So we can identify polynomials of degree strictly less than m with vectors of with m coordinates, and the map is evaluated polynomial. So now, as I said before, this polynomial space is a very natural, obvious basis, namely increasing powers of x, starting with the 0th power up to the m minus 1st power. But on the other hand, this vector space fq to the m also has a very natural, obvious basis, where you just pick the standard basis, where you have a 1 in certain coordinates and zeros everywhere else. So let's say E1 up to EM. That is a very natural and obvious basis on the right-hand side. But these two do not immediately play together. So the evaluations of these powers of x, they give rise to these rows in the van der Monde matrix. While then, if you go the other way, there should be polynomials that evaluate to the standard basis. And indeed there are, and it's not so hard to write them down explicitly, which I will do in a moment. But what you get is the so-called Lagrange basis of the polynomial space. So if we simply pick the inverse of the evaluation map of the ith standard basis of fq to the m, we should get a polynomial. It's going to have degree at most m minus 1. In fact, it's equal to m minus 1. And it has the property that if you evaluate Li in xj, you get the Kronecker delta function of I and j. So it's 1 if I is equal to j and 0 otherwise. Now, okay, so this will have to be a basis, an alternative basis for your polynomial space. And if you want to write down what this polynomial actually is, well, you simply take the product of the variable capital X minus XL, but you leave out the ith evaluation value. And so this will already make sure that you get zeros as long as I is not equal to j. And then you divide by the appropriate value to make sure that you get a 1 if you evaluate Li in xj. So in other words, we are going to get the product from L is 1 to m, L not equal to I, of x minus xl divided by xi minus xl. So that is going to be the ith polynomial in the Lagrange basis. So, okay, so indeed note that the degree is equal to m minus 1, and simply inserting these evaluation values, you check that you have the right property. So these can now be used to get a systematic generator matrix of a Reed-Solomon code, simply because you can now evaluate those k polynomials. So now I'm applying this for the case where the parameter m is equal to k. If you pick these k polynomials, they're now going to have degree k minus 1. So then we will have again, a basis of our codes, of the Reed-Solomon codes, and this, by construction of the Lagrange basis, the first k by k block will now be the identity matrix, and then something else will be added after this. So in this way, we can find a systematic generator matrix. And again, the choice of the particular points to construct your Lagrange basis for was irrelevant. So we could have placed this identity matrix for any k columns of our choice. Okay, so that is a nice thing. And why is a systematic generator matrix actually interesting? Well, there are maybe several possible answers. So here is one possible answer. It is that if you now encode, so I mean, for an error correcting code, mathematicians would typically say this is a subspace of fq to the n, a linear subspace of fq to the n. That is correct, but if you are a little bit more in this application of error correcting codes, what you first have is a message which consists of k coordinates, and you need a way to associate to a message with k coordinates a code word with n coordinates. And what you typically do in general is you pick a generator matrix and you multiply these k message symbols as a row vector from the left with your generator matrix, and out comes a code word with n coordinates. So this encoding going from message to code word is basically just a vector matrix multiplication. If you pick a systematic generator matrix, the good thing is that the first k coordinates of your code words are simply going to be your message, k message symbols. And then you add n minus k additional symbols to it. So in a systematic generator matrix, you can recognize the message immediately by just looking at the first k coordinates. And this can have its advantages even for decoding. If decoding completely fails, you can at the very least return the first case coordinates with the warning that decoding failed. But at least you can do something. And this can be better than the alternative, which would be to ask for a retransmission or something like that. So that is one reason why it's interesting to have a systematic generator matrix. Another possible answer is already has been addressed by the previous speaker. If you have a systematic generator matrix, it is easy to construct a parity check matrix. So in fact, knowing this form of a systematic generator matrix, can immediately write down a parity check matrix as well. So that is another interesting property. And why actually do we care about parity check matrices? Well, in the first place, it gives an alternative description of the code as the kernel of a certain matrix. But we can also think of this in this more concrete setting of error correction, where you receive a word, and maybe you want to figure out, is the received word actually a code word or not? Because if it is a code word, it's most likely that no errors have occurred and you don't have to worry about decoding at all. So having a parity check matrix, you simply multiply with the received word. If the outcome of that multiplication is a zero vector, you know it is a code word. It's even only if, in fact. So that gives you a very quick way to detect errors. If this parity check matrix times the received vector, if that gives you a non-zero output, you know something is wrong. You know an error has occurred. And this product is usually called the syndrome. It's called the syndrome, even though it depends on the choice of parity check matrix. But anyway, now I'm really digressing. So a parity check matrix is in principle easy to compute, and it solves the problem of error detection completely. So error detection is easy to achieve. The error correction, that is what is causing the headache typically. Okay, so this Lagrange basis can be used to compute a generator matrix in systematic form. Okay, now I also want to use this Lagrange basis for the space of polynomials up to degree n-1, because it will allow us to construct a parity check matrix. But hey, wait, I just said we already know how to construct a parity check matrix. So that's fair enough. So the real reason for this is not to construct a parity check matrix, because we already know how to do that, but it is to say something about the structure of a possible alternative parity check matrix. So I'll go through all the details in a moment, but what I want to emphasize is that the outcome will be is that essentially a possible parity check matrix of a Reed-Solomon code is again one of these truncated van der Monde matrices. The only snag is that we will have to multiply with a diagonal matrix whose entries are non-zero. So the effect of that multiplication is that compared to the effect is simply that the columns are going to be multiplied with the elements on this diagonal. So Sudhir already introduced the notion of a dual code and then talked about the McWilliams identities. So the dual code, by definition, will have the parity check matrix as a code as a generator matrix, right? So we started here with the Reed-Solomon codes. I'm going to compute this form of a possible parity check matrix, but that means that the dual of a Reed-Solomon code will have this as a possible parity check matrix. So in particular, we can immediately conclude that this is very similar to a Reed-Solomon code. I mean, if this diagonal matrix wouldn't be there, this would be a Reed-Solomon code. So for this reason, it's quite common to slightly extend or generalize the notion of a Reed-Solomon code to something which is called a generalized Reed-Solomon code, where you essentially take a Reed-Solomon code and then multiply each column independently with a non-zero element from the finite field. So in other words, it would exactly mean that you multiply with such a diagonal matrix. So what that means is that this whole thing here is actually the generator matrix of a generalized Reed-Solomon code. And then it's not so hard to see if I would have started with a generalized Reed-Solomon code, the dual of that would still be a generalized Reed-Solomon code. So that is a nice class of codes that is closed under taking duals, so to say. So that is one outcome of this. And that in turn will mean that also the dual of a generalized Reed-Solomon code is going to be MDS. But of course, as already posed as an exercise in the previous talk, the dual of an MDS code is always going to be MDS. But this is a way to see it for Reed-Solomon codes and generalized Reed-Solomon codes. So, okay, so one more observation before I talk about the technicalities here. So why would we expect that the dual of a Reed-Solomon code looks so much like a Reed-Solomon code again? Is there, I mean, we're going to see why, but is there a more structural reason for this? And since the organizers have been so generous with time, I want to take a few minutes just to talk about that. So Reed-Solomon codes are evaluation codes, meaning that you obtain them by evaluating certain functions, in this case polynomials up to a certain degree, in certain elements from FQ, from the finite field with Q elements. Now, there's another way of looking at this. Just as you can think of the real numbers as a line, you can also think of FQ, a finite field with Q elements, as a line. And a line is a geometric object. And this really means that what would happen if instead of a straight line, I replace this geometric object by another curve, so an algebraic curve. And also in that setting, you can talk about evaluation codes. You can pick a suitable subspace of functions on your curve and define something which is called an algebraic geometry code. Now, the algebraic geometry codes, they are more complicated, in some sense better, with better parameters, but what algebraic curves come with is a lot of known theory. They come with a lot of algebraic geometry behind them. And one of the nice things is that if you take this more abstract point of view, you can see that the dual code of such an algebraic geometry code, when obtained by evaluation, is something related to it, but this time you will need differentials on the curve, and then you get code words by taking residues of those differentials. So don't worry if you don't understand what I'm talking about. It's not really important for the second lecture at all. But I just want to mention that if you take a more general point of view from AG codes, then you can see dual codes in a different way. And then one can actually show that these differential codes you can obtain can also be described as evaluation codes. So there's a completely general machinery where you can see what is going on. And this will specialize in this case to the fact that a generalized Reed-Solomon code will have a code of similar type as a dual. So there is a better explanation as to why this happens. Another advantage of this AG code point of view is that it allows you to create generalized Reed-Solomon codes of length up to q+1. So this construction we have here really tells you that you can go up to length q, but that's the end of it. But in fact, you can just go to length q+1, and the simple reason is that a line, when you see it as a projective object, it will have an additional point at infinity, so to say. So there's an additional possible evaluation point, so to say. Okay, I think I've digressed enough. I just wanted to make these points because it's nice to see connections with other areas. So, okay, so how do we create this parity check matrix? So typically what we will need are equations of the form, what we need is to create a matrix of the right size, so n minus k times n, such that this parity check matrix H times the transpose of the generator matrix gives you 0. I mean, that's going to be the defining property. So we somehow need to find equations of that type. And this G here, we're going back to the Van der Monde generator matrix now. So here we know that the elements in G are going to be powers of your evaluation point. So you have to try to find equations of that type somehow. And the key is going to be to look at a Lagrange basis, this time of polynomials up to degree n-1, because these are going to give rise to identities of that type. So we start with a polynomial identity. So I'm claiming that if I have an exponent j between 0 and n-1, I can rewrite this power of j in a Lagrange basis. I mean, that is clear because this power basis and the Lagrange basis, they are both bases of the same space of polynomials up to degree n-1. So there must be some linear combination of the Lagrange basis giving this x to the j. But actually what the claim is that the coefficients are the powers of the evaluation points I took, xi to the j. So that is a nice property they have. And the proof is not hard. It is an identity that looks a bit, if you've never seen it, you may think, where does this come from? But this is simply because if we evaluate everything, then this Lin of x is going to be replaced by the ith standard vector. So that means that if I look at the specific coordinates, then what I'm going to get is xi to the j, because all the other polynomials, when evaluated, will have 0 in this ith coordinates. So the ith coordinates after evaluation of the right-hand side is going to be xi to the j. And clearly the same is true for the left-hand side. If I evaluate x to the j in xi, of course, I get xi to the j. So left and right-hand side will be the same when evaluated in all the n evaluation points. And then the polynomials will have to be the same as well. So that is a very simple proof of this nice identity. And this identity actually pops up not only when converting power bases to Lagrange bases, but also I've seen this once in a while in algebraic number theory. There's something called the complementary module, and if you study that, also this identity comes in. So let's work out what this gives us in terms of equations. So here we have an identity of polynomials. So it means that we can now zoom in on any power of x we want and compare right and left hand side with each other and try to figure out what we have. So for example, if we now pick the coefficient of x to the power n minus 1, well, on the left-hand side, that is very simple to determine because it's going to be 0 unless j is equal to n minus 1, in which case it would be 1. So let us pick the j for now strictly less than n minus 1, so something between 0 and n minus 2. So then we know that on the left-hand side here, the coefficient of x to the n minus 1 is 0. Okay, that's easy. So what is the coefficient of x to the n minus 1 on the right-hand side? Well, we have seen that these polynomials Li of n, they have degree n minus 1. So it's actually not so bad to figure out what the coefficient of x to the n minus 1 is on the right-hand side, because it's somehow, we just have to look at the leading terms of all these Lagrange basis polynomials and then multiply with xi to the j. And if we do that, so remember how these Lagrange bases were defined, we had to multiply a bunch of linear factors with each other and divide by values to force the evaluation to be 1 for xi. So if we are only interested in the leading term of this polynomial, so we can ignore this minus xl here, we simply get the denominators multiplied with each other. So this is going to be the leading term. This 1 divided by this product is the leading term of Li, and I multiply with xi to the j, and apparently this adds up to 0. And if we would look at other coefficients, you get more complicated identities. But we won't need those. If j is equal to n minus 1, we won't need that either today, but if we would do that, we simply get that a similar summation is equal to 1. That's the only difference. So this is kind of the type of identity that is nice to have. So now let us just play a little bit with it and say we have a gamma I, this whole denominator, let's denote this by gamma I. So gamma I is 1 divided by this product. And if we do that, then we can actually figure out the parity check matrix. So the claim is that these gamma i's are going to be our column multipliers. So those are the ones on the diagonal, and we need the Van der Monde matrix in front of it. So let us see why this is true. So we have a Van der Monde matrix now for G, and for H we have this guess. So let us figure out what is going to be H times G transposed. So we simply compute the ijth coordinate of it. So we can use basic matrix multiplication and figure out what is going on. And what we end up is a summation over L of xl to the I minus 1 times xl to the j minus 1 times the Lth column multiplier times gamma L, in other words. So the nice thing is that we have the same variable xl occurring, so we can just add up the exponents, and we get the exponent I plus j minus 2 here. And now the question is, what can we say about this? Well, everything just works together nicely, because if I is strictly less than or equal n minus k, and the same is true for j, then the sum is going to be less than or equal n minus 2. So it means that this corollary indeed applies, and I can simply use it and conclude that I do get 0. So indeed, the right kind of identity is satisfied. H times T transposed is going to be the 0 matrix. And what about the rank? Does H have full rank? Well, this Van der Monde matrix certainly has full rank n minus k. And looking at these gamma i's, we can see that these are all non-zero elements. So this diagonal matrix does not change the rank at all. So H is the right thing. It has rank n minus k, and the product is 0. So here we see what it means concretely to show that the dual of a Reed-Solomon code is essentially a Reed-Solomon code again. And that is a nice thing to know, especially from the structural point of view of algebraic geometry codes. Okay, so I think rather than starting with the decoding now, I realize I have a little bit of time left, but I think it is better to do then the entire decoding in the second lecture. So I think I will stop now. Thank you. If there are any questions, feel free.
Okay. Thank you, Peter. So people can ask questions either by typing in the chat box or just unmuting themselves and speaking. We have time. Of course, it's a long day.
Yeah, no, it's fine.
So maybe I'll ask a question, which might. So you interchangeably use the word Reed-Solomon and generalized Reed-Solomon.
Yeah.
What's the difference between the two? I don't remember if you explained that or.
Yes. I mean, technically the difference is that a Reed-Solomon code is one you obtain by evaluating polynomials up to a certain degree in n distinct evaluation points.
Yeah.
And a generalized one is where you additionally allow to multiply each coordinate independently with a certain value, with a certain scalar.
I see.
But of course, the distinction problem is slightly subtle, but you can again use this, as you mentioned, the reduced row echelon form if you want to figure it out. But of course, the essential things are the same. The minimum distance is the same. Decoding is going to be essentially the same problem, and the weight distribution is the same. I mean, it's an equivalent code.
So I guess that's what you're saying is it's a monomially equivalent to the Reed-Solomon code for suitable choice of constants, non-zero constants.
Yeah, exactly.
Okay.
So, is it correct to say that the arc is the same in a projective space?
Yeah, I think so. Yeah, I mean that would be the same as a monomially equivalent class of a Reed-Solomon code. Yeah.
And then if the extended one is you add.
Yeah, it would be a normal rational curve, right? In the Reed-Solomon.
Exactly. Well, that would be the extended.
Fair enough.
Yeah, I don't know, Michelle. I mean, I think for younger people in the audience here, this arcs and so on is a language in finite geometry, which is very, very closely related to MDS codes and the Reed-Solomon codes, etc.
So there is a question in chat.
Oh yeah, there is. Okay.
Yeah. Okay.
You can see that. Okay.
Yeah, I can see it. I mean, one can, but I'm not really an expert in that. So I'm not sure what really happens there. I have never really worked with codes over rings, unless they happen to be fields.
Any other questions? Prashant, did you have a question or?
You're muted. I can't hear you.
Unmute, Prashant.
Okay. Maybe in decoding, I'll have something, not today. I think today I'm fine.
Okay.
If there is time, maybe not immediately related to what you were saying, but just general in terms of applications. Are these codes used? Are these codes still used? Are they still relevant?
Yeah, they are still used. So I even have a list of applications somewhere, current applications. No, but one of them I know by heart is they are used in Blu-ray discs. So the reason they are still used is that, as we will see in the next lecture, they can be decoded fast. And they can be decoded with up to a certain error limit with 100% guarantee. So because of these two reasons, they are still used. Yeah. So what is typically done is actually to arrange, so to say, Reed-Solomon codes in such a way in a matrix form that so that each row and each column is a Reed-Solomon code word. And then maybe, in fact, you go to this BCH subcode. But anyway. And then what is done is you can use this Reed-Solomon decoder to correct each row, afterwards correct each column, and then iterate this a few times. And then you can actually correct with high probability now very many error patterns. So in this form, they are still used quite a lot. Yeah.
And maybe a follow-up question then. Do you also know of examples where they were used in the past, but they have now been replaced by better codes?
I mean, preferably I would check. So yes, there are examples, but I don't want to tell something that is wrong. But I think there are situations where they used to have a combination of convolutional codes with Reed-Solomon codes, where now they use LDPC codes or polar codes. But if you really want me to pinpoint a concrete setting, I would have to look that up to be sure. But yes, they have been used more extensively in the past. That much is true to say. But it looks like they're not really going anywhere just yet, on the other hand.
So what are the weak points? Like, what are the reasons why they were replaced in these examples? I mean, I know I'm really pushing you here, but
no, but I think the main reason is that I mean, what you want is to have some coding scheme that comes close to something called capacity of the channel. And then preferably avoid non-binary finite fields. So it is nice if you can simply work with binary codes. And then there are these LDPC codes that at least experimentally come close to that, to reaching channel capacity. Having a very cheap and easy decoder. So then in those kind of settings, they have phased out.
Thanks.
Yeah. So I guess one drawback is for Reed-Solomon, the field size has to be pretty large. Binary, you hardly have any Reed-Solomon.
No, I mean, that's the thing. So then you would have to go to BCH codes.
Yes.
But these are, of course, no longer NDS, so there you lose something. But indeed, that is the main drawback, unless you happen to be in a situation where that is an advantage. I mean, there's something called a burst of errors, where if an error occurs, it's likely that many in a row occur. And then it might have been good if you have clustered together many bits in one finite field symbol. because then this error correction will correct these clustered symbols in one go. So that again, that is on a very specific case why they have been used and probably still are used on Blu-ray discs.
So there is a question I see in the chat box from Varsha.
Yes, so what's the advantage of an MDS code? You mean, well, so I would say in general, if you are using a code and your goal is to have, to know for sure you're going to correct up to a certain number of errors. So then it is good to have a code that has a large minimum distance compared to its length and dimension. And then an MDS code is the best you can do because it reaches the singleton bound. So you cannot do better than that. But I would say that is what is important for this decoding point of view is that you can decode fast. So therefore Reed-Solomon codes are so interesting, and these happen to be MDS. But if your question is, could you replace the Reed-Solomon code by another MDS, then that really depends if you can still decode fast.
Yeah, I mean, I did not say it, but roughly speaking, if the minimum distance is D, then you can correct D over 2 errors. So they are part of that many errors. So, so it's kind of natural to want to have that minimum distance as high as possible. And MDS, for the given length and dimension, that's the highest you can.
Yeah.
Let's see, any other questions or comments? Looks like none. So let's thank Mr. Peter Whelan for a very nice talk. Thank you very much. And so now we have one more talk to go. Yes. So we have half an hour break. If you like to have early dinner in India, you can have that, or you come back to us at 8 o'clock Indian time and translate it to appropriate time wherever you are. Basically, half an hour from now. Thank you. Thank you. Bye, Peter. Thank you.
I have to go, Sudhir, also.
Yeah. Bye.
I will see you tomorrow, hopefully.
Sure.
Hello, Pante. Hi. I think you have to unmute yourself. You need to unmute yourself. We can't hear you actually.
So what he says is that you asked to join, but somebody has to let you in.
Yeah. I just called the concerned person, and perhaps they have, yeah. Okay.
But he was early enough that we, we could resolve these issues.
Yeah. I'm just getting a call.
Yeah, hi Pante. This is Sudhir.
Good morning.
Good morning. Of course, it's late. Yeah. So you're up and about at what, 6 in the morning already?
Yeah, it was 5:45 when I woke up actually.
Okay.
Oh, I see some of my friends there. I see Bimal Mondal and.
Okay.
Yeah. I probably should try to see if I can share my file.
Yeah.
Yeah, we still have 5 minutes, so I expect more people will join. Okay, looks good.
Did the scrolling work?
Yeah.
Perfect.
It did.
चलो यार मैं चलता हूँ ना.
So Sartaj, you will introduce the speaker.
Yeah. Still, there is 1 minute to go. So
yeah. 2 minutes in my.
I tried to stay until Bimal Da actually gave his introductory talk, but I just couldn't.
Oh, you then okay, I did see you. Okay. Yeah, I mean, I'm sorry the timings are extremely odd for you.
Well, usually you travel, right? You travel to places and then. But it is what it is. I mean, we have to do the best that we can under the circumstances. So it's about time, I guess?
Yeah,
it's time. So shall we start?
Please start.
Okay, so it's my pleasure to introduce Professor Panteleimon Stanica. So he's currently professor and associate chair of research in Applied Mathematics Department at Naval Postgraduate School, California, USA. And he's also associated with Institute of Mathematics of Romanian Academy as a researcher. He's a well-known expert in the area of cryptography and also in number theory. I mean, of course, he does not require any introduction, but it's good to formally introduce him. He completed his PhD from State University of New York at Buffalo in the year 1998, and he's also a co-author of a very famous book on Boolean functions. And the title of that book is Cryptographic Boolean Functions and Applications, which is a quite popular book among cryptography community. And of course, he's a renowned researcher, well-known in the community. With this brief introduction, I would like to request Professor Panteleimon Stanica to begin with his first lecture on the introduction of cryptography, which would be consisting of some classical ciphers and some historical account of cryptography. So
thank you so much. Yeah. Thank you so much, Sartajan, for allowing me to speak and for inviting me to speak to the conference. As I mentioned earlier, obviously it's easier to attend and interact with researchers when you're present there, but we do the best that we can under circumstances. So I decided to do this historical look on cryptography because sometimes we forget about where some of the concepts and some of the methods are coming from. And you will see, some of the things actually that we currently use, like autocorrelation and things like this, they were around for hundreds of years. So I decided to do this historical look on cryptography. Well, we use various terms to refer to areas of cryptology and surrounding areas. For instance, cryptology studies communications and protections over RCK channels, and it includes cryptography and cryptanalysis. The cryptography is the process of designing the systems, and cryptanalysis is breaking such cipher systems. Coding theory actually is the encoding, the studies communication over noisy channels, sometimes, unintended, sometimes intended noisy channels, and ensuring that the received message is the intended one. Now, the scenario is actually quite clear. Alice sends a message to Bob, for instance, and Eve, Oscar, Mallory will try to corrupt, masquerade, break the communication. The breakage actually is the breakages of various types. It could be just to destroy the communication between the two. It could be just to find out the communication between the two, whatever the case may be, okay? Now, sometimes, well, not all the time, when we actually look at crypto systems, we have to take into account Kirkus principle, which is a 19th century principle. One should always assume that the method used to encipher is known to the opponent and that the security must lie in the choice of the key. This does not necessarily imply that the method should be public, just that it is considered public during its creation and assessing. Okay? Now, what is the advantage of the open cryptography design? Because we actually get these questions all the time. Why is NIST, National Institute of Technology, in US or the European standards actually are, calling for these standards, why do they have to actually be open? I mean, why do we have to assess them? I mean, why can't they be secret? Well, because there's some advantages to open cryptographic design. They undergo public scrutiny, and they are likely to be stronger. We have to also have confidence in the security of the scheme if it has been, it was studied actually in the incipient stage and no weaknesses have been found. It is obviously better for the security flaws if they exist to be revealed by ethical hackers and possibly fix them. Now, there are instances when the system actually was kept secret, but there was reverse engineered. The code was reverse engineered and even published online, for God's sake. Okay, so this is how we actually establish the standards, public design at the end of a call for such a proposal. All right, now the key space. This is actually what we that's what we know how to count, right? The key should be chosen sufficiently large so brute force attack searching through the entire key space is infeasible within an acceptable time period. Now, many, if all, perhaps all ciphers can be broken by brute force attack. Well, you may say, well, but hold on a second, that's kind of difficult, right? Or that's kind of scary. Well, yeah, but if you have to spend more than the actual, life of the universe, 10 to the power, 15 years or something like this, then of course that's as equal, in my perspective, to unbreakable, right? Not all keys are created equal, mind you. Just to give you a glimpse into this world, you will see here some of the key sizes for some popular actually ciphers, and this is a preview for my lecture tomorrow on data encryption standard in AES and some other ciphers, block ciphers. So for instance, 56 bits, which was the key size for data encryption standard, adopted in the beginning of the 1970s or mid 70s, and phased out in 2000, around 2000. Now, we consider that to be broken because you can design a system, for instance, that can break it in a few hours nowadays. On a regular computer, 128 bits or 192 or 256 bits, which are the three key sizes for advanced encryption standard, will take quite a few years. For instance, 256 bits with top secret for advanced encryption standard may take, even if you check 10 to the power 23 keys per second, it may check more than 10 to the power 46 years. Of course, nation states could probably go through that space, but it's still, infeasible currently to go through that space. So there are many applications of cryptography. Confidentiality, of course, you should not be able to read the message sent by Alice to Bob. Integrity, data integrity, Bob should be confident the message he received from Alice was not altered by Eve. Authentication, well, he should be also certain that Alice was the one who sent the message. Authorization, well, Alice grants Bob some privileges, right? Non-repudiation, Alice cannot claim she did not send the message to Bob later on. There are two types, for instance, symmetric ciphers, or the two types of ciphers, symmetric ciphers and asymmetric. The symmetric ciphers, knowledge of one key reveals the other key. In the case of asymmetric, or sometimes for public key, crypto or systems, the knowledge about the encryption key does not reveal the encryption key, and vice versa, without some extra information. Let's go back a little bit in history. Now, cryptography comes from a Greek word kryptos, which is hidden, and graphy, which is writing. So hidden writing basically means. Now, early encryption began around 1900 BCE, right, before Common Era. For instance, the pharaoh Amenemhet used hieroglyphic substitution to impart dignity and authority to the inscriptions of the pyramids. And around between 1500 and 500 BC, Assyrians actually began hiding information. Tattoos, they would shave the heads of a slave, for instance. They would tattoo the message, and they would wait for the hair to grow out, and they would send them out to the recipient. They would carve messages on animal stomachs. They would actually hide messages on the new wax, and so on and so forth. These were the messages, again, quite a few thousand years ago. In 600 BC, Hebrews actually described a simple substitution cipher called Adbash, using the reverse alphabet, the book of Jeremiah. I have to mention actually one of the 64 arts in Vatsayana's Kama Sutra, for instance, 2nd or 3rd century Anno Domini, Mnahita Vikalpa, which was also the art of secret writing and communication. Vararushi actually, it's an Indian cipher probably dating to 4th century AD. In 8th century AD, Arabs actually were the first to discover and write the methods of cryptanalysis. Now, during the Middle Ages, the encryption was primarily in Europe. Encryption was primarily restricted to the monks, so they were the ones who actually had the knowledge, and they were obviously at the time they were able to write and read more so than the regular folk. Now, the two types of ciphers that we meet a few hundreds of years ago, transposition cipher and substitution ciphers. In transposition cipher, we basically take the plain text and we scramble them according to some, some method, some key, and this corresponds to Shannon's principle of diffusion. Again, you will see these were spelled out, obviously not in 400, 500 years ago, rather just 70 years ago. The relationship between the plain text and ciphertext must be as complex as possible. For instance, Kittel, about 500 BC, was such a method. For instance, you take a rod of a certain dimension and diameter, of course, and you write a message or on a piece of leather, of course, around that time, and you wrap it around you wrap the message, the piece of leather around the rod. You write the message, and when you unravel that, the letters are scrambled. Of course, this is obviously transposition because you don't change a letter by a different letter. You scramble them according to some method. So I scrambled here. This is a talk on early cryptosystem given RRU. And of course, I took the dimension, random dimension. Then when I unwrap it, this is basically my ciphertext, the one on the bottom there. Now, substitution cipher, it's slightly different. We replace the plain text letter with other letters. Of course, the resulting text, the ciphertext, and the method to do so is the key. It does correspond to Shannon's principle of confusion. The relationship between the ciphertext and the key must be as complex as possible. You see, the two principles that I just mentioned to you, diffusion and confusion, are quite vague.
It seems that your slides are not getting changed, or maybe there is a problem with me, I think. Okay.
Can anybody confirm that they are getting changed?
Yeah, now I can see a different slide. Yeah.
What about now?
Now, yeah, it's so we are at substitution cipher.
Yeah, so probably it was somewhere at the end there.
yeah.
All right. But thank you for letting me know. I mean, if something happens, I'll obviously prefer to know about it. Now, these principles that I mentioned, diffusion and confusion, were spelled out in the, as I mentioned, 1950s, 1949 precisely, by Claude Shannon. He did introduce some good crypto properties like diffusion and confusion and spelled out in this paper, Communication Theory of Secrecy Systems. He probably, it's available online. You can download it and see the incipient stages of modern cryptography in some sense. Now, Caesar cipher, which was done again in about 50 or 70 BC, it was actually one of the ciphers that Julius Caesar actually used to correspond with his generals, but it was a very simple one. It was just a simple shift by 3. But please remember that this was before Common Era, so it was 70 BC, and obviously not a lot of people knew how to read. So literally, you just take the plain text and you shift every letter by 3 to the right, and of course, the description would simply be shift to the left by the same amount. So you may think, well, but this is an exercise in futility. Well, believe it or not, this was actually done in an operating system a while back. not as a secure system, mind you, but it was just an implemented cipher. It was called ROT13. So if you remember OpenBBS a while back, well, I'm old enough to know it. OpenBBS had the ROT13. Of course, in English, 13 is a divisor of 26, which is the number of letters in English. And that means that ROT13 would be actually able to use for encryption and decryption. So the same command, you would go to the online, to the prompt there, and you say ROT13, and you take the plain text, and you would encrypt it, and ROT13, the cipher text, and it would decrypt it. Just because moving to right by 13 and moving to left by 13 is the same thing, right? Now, you can certainly generalize this. I mean, you take that simple cipher, Caesar cipher, and you say, well, how can I make it stronger? Well, instead of actually shifting it by 3, you can shift it by anything, and also multiply the plain text by, again, when I say multiply the plain text, you encode it. Either use the simple encoding, 0 is A, and where A is 0, B is 1, and so on and so forth. What you do is you use ASCII, for instance, to encode also the punctuation and the spaces and so on and so forth. So ASCII code could be used as well. I mean, whatever the case may be, you can use either one of them. So you take the plain text letter, you multiply it by some multiplier, and you shift it. And of course, you reduce the modulo, whatever the size of your alphabet is. I'm taking English as an example there, 26. Of course, to be able to decrypt it, you'd have to take the multiplier to be co-prime to the size of the alphabet. Otherwise, you cannot actually decrypt it, right? So because decryption is A inverse CI minus B. Of course, you move the B in here and so on and so forth. So it's a simple, first grade probably, or some lower grade mathematics. Again, we know that A has to be co-prime to 26 for this to be invertible. The key space, I mentioned to you that one of the things actually we do when we design a system is count the key space. Count the size of the number of keys, see what the size of the key space is. In this case, you have 26 choices for B, and you have verify function of 26 because that's the number of co-prime numbers. Please.
There appears to be a problem with the slides again. A lot of people are writing in the chat box, in fact.
So does it move now?
Now it's moving, yeah.
I don't understand this because it seems that some people actually are seeing it, some people I don't see it, but you know what?
I'm getting a lot of messages in the chat box where people are, now it's okay, now it's working.
Okay, so let me scroll through it and not screen it. Again, so verify function is, remember, counts the number of co-prime numbers to 26, and of course that means that the number of choices for the pairs A and B is 26 times phi of 26, which is 312. It's too small to be practical. You can probably break it while driving. Now, some of the early ciphers, we meet them in Europe, actually around 1500 or 15th century. Leon Battista Alberti actually is sometimes called the father of Western cryptography. He developed a cipher machine, and again, we'll see that quite a few, 500 years after, for mechanical encryption. He also developed and published the first polyalphabetic cipher and design a cipher system to simplify the process. Okay, there are many other codes. For instance, if you look online on whatever sites, FBI's, for instance, site, you'll see some of the pager codes, some of the drag traffickers codes they use, telephone keypad codes, sport bookmaking, horse race bookmaking codes. You will see some of the codes even in the literature. I mean, even Jules Verne, for instance, and this is well known, he actually had a cipher code. Basically the positions of a human would encode every letter in whatever alphabet. Using hands and positions and so on and so forth. You will see Masonic ciphers and so on and so forth. Now, moving forward by 400 years, 500 years. We see the Mexican Army cipher disc. This was invented in 1913. Basically, there were several ciphers. 5 discs. 4 discs was actually for encryption, and 1 for plain text. And the way you actually move the disk together, you will know how to encrypt every letter. For instance, a letter could be encrypted by many choices. For instance, A could have been encrypted by 24, 41, 56, or 99, depending upon the positions, okay? So apply math at MPS, AM and PS could be encrypted 24, 68, 11, 71, 91, because A corresponds to 21, 41. So I chose 24, but I could have chosen 56, for instance, as you see here. So this is, again, 20th century. Again, Mexican Army cipher disk. Now, again, moving a few years, in time, further in time, we see the rotor cipher machines. And this was invented by two Dutch naval officers, Hengel and Spengler, for instance, the rotor cipher machine. And they use a typewriter-like keyboard for input and lighted letters for the output. Again, it's just an incipient, not quite computer, but electric machine. Now, Enigma, which is well known, was designed by Arthur Scherbius around 1918. He actually used the 3 interchangeable rotors which were geared together. Of course, there were 26 cubes, 17,576 combinations of letters, but every letter could have any permutation. So, of course, that means 26 factorial cubed. It increased actually the number of possible settings to a gigantic number. Again, remember, this is the beginning of the 20th century. 159 million keys, right? So, again, no computers at the time. If 1,000 cryptographers, each with a capture enigma, tested 4 keys per minute, all day, every day, it would take 1.8 billion years to try them all. I like to do this actually all the time when I look at the size of a key space, just to put it in perspective. I mean, as I mentioned to you, the expected life of the universe is between 10 to the power 12 and 10 to the power 16. Of course, nobody would know, but that's what physicians actually are telling us. So 10 to the power 12, 10 to the power 16 years. Well, some of the, crypto system that we currently use, even if you use the best attacks on them, it would take more than the expected life of the universe, right? So that's why, I like to say that. Of course, we can also put it in perspective with the number of particles in the universe, which is, people say it's about 10 to the power 80 or something. So if the key space is bigger than that, obviously that gives us more confidence in it. That's why, to try brute force on some of these ciphers is really not the method to go. Okay, and I'll tell you why. So let's take the substitution cipher that was considered unbreakable for about 350 years, mind you. Again, the key is some permutation of letter. Is not necessarily a shift; it's just a permutation. Of course, we know from our elementary math classes that the number of permutations on, let's say, English is 26 factorial, which is more than 2 to the power 88 possible keys. Of course, 2 to the power 88 cannot be done on a personal computer, even on a supercomputer. I mean, you can go through a space of, obviously not the nation-state supercomputer, but a regular supercomputer that can exist at a, university or whatever. It can go up to 2 to the power 60 maybe. Okay, so 2 to the power 88 is quite a lot of keys. But you can actually be smarter than that, right? You can be smarter than trying every single key out there, every single permutation. So for instance, let's say I know this ciphertext that you have on your screen. I know it looks, scrambled, and how do I come up with, of course, I made it a little easier by respecting the orthography, the punctuation, spaces, and so on and so forth. So it makes it a little bit easier. Of course, in reality, if you were to do this for real, you would actually concatenate all these words and make it slightly harder. Okay? Now, again, obviously, you cannot try all 2 to the power 88 possible keys, but we can actually be cleverer than trying every key. We can do statistical analysis. One thing that we actually have to do to realize is that every language, independent of whether you know it or not, is not random. I mean, it may seem random to us, if we don't speak it, but it's actually, they have rules. So randomness is quite clear to define, for a certain alphabet, but language is not random. And you will see later on, for instance, an analysis on some of the languages that you know of, and even Hindi I put, for instance, in there, and some of other languages, that you will see a jump of about 2 factors between random and the intrinsic, actually, non-randomness of a language, okay? For instance, in English, E is the most common letter, followed by T, followed by A, and O, I, S, N, H, and so on and so forth. So there is actually, even if you do check, of course, language evolves, but if you check, for instance, the Library of Congress in the US, with the books that were published in the beginning of the 20th century, not 21st, 20th century, and you do the analysis, count, for instance, you take a random book or thousands of books or millions of books, and you count, for instance, the number of occurrences of E and T and so on and so forth, they respect the same actually scale in spite of the fact that the language evolves. So in spite of that, they respect. So I've had students actually who did this analysis for me on a book that their wife preferred, for instance, or husband preferred. So they took a book and they digitized that and they count the number of occurrences for E and T and so on and so forth. And regardless of what the book is, of course, there's some books that actually avoid that. There is a famous book where E is avoided completely. But it was just a made up. If you don't do that on purpose, then of course any book would do it. So how can I use this intrinsic property of a language to cryptanalyze such a text? For instance, again, you cannot do it if the text is very, very small, but and this is of course made up. So for instance, for this text that I have right here, I'm counting the number of occurrences, assuming that the simple substitution was used. I'm not counting the number of occurrences for each letter. I'm seeing that W is occurring 20 times, C and F and G occurring 11 times, and so on and so forth. Assuming that I have the respective scaling there, of course, sometimes we have to change it. I'm assuming that W is actually E in normal English, of course. And believe it or not, that's going to happen for this particular text anyway. Of course, sometimes if the occurrences counts are close enough, you may be off. But you don't do this by hand. You use a Java applet, or nowadays we can use a semi-hybrid system, human intervention and a computer system, and of course that's gonna work out quite well. Okay. But you don't have to do it only for letters. You can also use, for instance, groups of letters. There was a while back, I remember maybe 15 years ago, where you could actually buy from Google, you could buy, statistics analysis of diagrams and trigrams and, pentagrams and sexagrams and so on and so forth. Nowadays, anybody can actually get them for free, so you don't have to pay for them. For instance, in English, TH occur more often than anything else, followed by HE and AT and so on and so forth. Again, these are groups of 2 letters, not necessarily words. And of course, trigrams, THE occurs more often, doubles and endings. So you can use all of these. And of course, if you have words, as I mentioned to you in my text, I separate them by the spaces in the plain text, then you can use that as well. All of this is intrinsic to a language, okay? Is intrinsic to a language, so you can use any such property, I can use the same in here, for instance, XBE occurs more often than anything else. So I'm assuming the XBE is actually THE. I already saw that W was, well, not saw, but I guessed that W was E. So of course, XBE makes sense that it's THE. I'm replacing throughout by THE and so on and so forth. So you can actually continue doing this. Obviously, it's painstakingly. I mean, it's difficult by hand, but with a Java app that can do it automatically, this is not, that difficult anymore, right? Remember, I mentioned to you that this this was actually a cipher that was considered unbreakable for 350 years. The simple substitution cipher. It was kept secret. It was actually the cryptanalysis was discovered independently by 2 people in the 19th century, but they were actually, I'll mention it a little bit later, but they was kept secret because of the Russian-Crimean War. So here's the plain text at the end of a process. Obviously, I would go through the entire process but time doesn't permit here. And you can cryptanalyze the text quite easily. Of course, human intervention. One thing that actually that I have to mention about the simple substitution cipher, which of course for security purposes we don't use, is because again substitution does not hide statistical properties of the plaintext, regardless of what the information is, what the language is. English and all natural language, in all natural languages that I have investigated, they are redundant. Some of the information that is revealed is actually redundant. So for instance, 60% of all the letters are redundant. I mean, if I were to give you that, the text right here, or the sentence, well, part of the sentence down here, you can still read it just because some of the, letters in there are redundant. We can still read it in spite of the fact that they are missing, okay? That's why we can actually cryptanalyze the simple substitution cipher. So how can we make it harder? I mean, people wonder that, Well, we can do cosmetics, obviously, concatenating the words and removing punctuation. You can even encrypt E with 12 different symbols like the Mexican army disc, right? So, every letter, depending upon the position of the discs, had could have been encrypted by different symbols. And of course, then counting is not anymore used. You can add some, interpurse actually in the plain text or in the ciphertext some noise, if you will. But you have to do it actually in a smart way, because the recipient has to be able to actually, remove that noise and recover the ciphertext and using the key to. So there are some constraints, of course. You can scramble the letters, of course, but one actually smart method is using multiple the same language but multiple alphabets. So using different substitutions for the letters depending upon the position that they have in the text. Okay. Now, Vigenère cipher is again one such cipher that was invented by Vigenère around in the mid 16th century, around 16th century, and it was again considered unbreakable for 300 years. It was broken by Charles Babbage in mid 19th century, but it was actually kept secret to help British in the Crimean War. Again, it was considered unbreakable for more than 300 years. More than 300 years. The attack was discovered independently by Kasiski, again, because they didn't publish, it was classified. So it was broken again. It was discovered independently by Kasiski, and you will see some of the methods used in there. In the beginning of the 20th century, a much better method was actually discovered. We just found out a few years earlier, literally a few years in 2000, maybe 14, 15, that there was the attack was also discovered in the classified community, but the young officer actually sent it to the higher powers, and of course the higher power did not see what they have in their hands, and they classified it somewhere and forgot about it. But I'll discuss exactly what the method is a little bit later. Anyway, so here's actually what you do. Vigenère is actually one method, one instance of the polyarithmetic cipher that is slightly easier to do, and it can be used in practice. It was actually used in practice by handing out literally a file to the sender and the recipient, and once they exchange the key with that particular page, the Vigenère table, they would encrypt and decrypt the message quite easily. So here's actually how it's done. It's done basically by, in English, for instance, you take a key of whatever size, n. I'll give you an example later on. And now you split up the plain text into modulo n being the size of the key, and then every single, every letter congruent to 0 modulo n, congruent to 1 modulo n, congruent to 2, and so on and so forth, would be encrypted using alphabet 1, alphabet 2, alphabet 3, alphabet n. Okay, well, if you start from zero alphabet up to alphabet n-1. So this is how the encryption would be, simply a shift. That's why it was simple to do it in practice, in the field. So a shift for every single alphabet of the plaintext depending upon the key. Okay, so it's easy to exchange the key via phone or whatever courier. And of course, the decryption would simply be done by shifting in the opposite direction modulo whatever the size of the alphabet is. So for instance, if let's say the key is MATH, math, obviously the size of the key is 4. If I have the plaintext secret message, I will encode this shortly, and then I will have the key 120197. Again, why? Because I'm simply encoding, not using ASCII, rather using A is 0, B is 1, and so on. Just to simply, argue and motivate what's going on there. And of course, modulo 26, if you shift E by 4 by 18, S by 18, you get that. E by is 4, your A is 0. Of course, you don't shift it, you get 4 as well. And you keep on doing this modulo 26. This is your ciphertext, EEVQA. What's interesting, as I mentioned to you, is that S is encrypted to E and E is encrypted to E as well. In other words, counting the number of occurrences for various letters doesn't work anymore. Okay, it doesn't work anymore. So Vision A just a series of case simple substitution ciphers. Well, of course, shifts, very simple. And you do Kosinski test. I'm going to, show you the cryptanalysis. Kosinski test, and for general polyalphabet cipher, you use Friesman index of coincidence, IC, which is much more complicated, is really a little bit of math involved in there. Of course, I'll do it once, you will see it once, and then you simply use the outcome, the final outcome, if you were to be faced with polyalphabet cipher in practice. Now, here's actually the Kosinski-Babbage idea between the cryptanalysis. So you have certain sequence of letters appears many times in the text, right? Now, a ciphertext that uses Vision A will have the sequence of letters showing in many places. So think about this. If you have 2 or 3 or whatever the strings, more than 3 letters, of course, appearing in the text, assuming that you use a polyalphabet cipher, right? Not simple. If it's simple, you can use the previous method to cryptanalyze it, use statistical, analysis of the natural language. But if they are neighbors, then they will be encrypted using the same sequence, possibly the same sequence of alphabets, right? So what you do is to come up with, for instance, again, the idea is that you don't know what the key is, but you don't even know what the key size is. Because if you do know what the key size is, perhaps you can actually do modulo the key size, and you can use the natural language on each alphabet. For instance, you take away, every sub-ciphertext congruent to 0 modulo n, if you know the size of the key, congruent to 1 modulo n, and cryptanalyze in parallel each alphabet using the natural language, and you put them together every single step just to see if it makes sense. Of course, it's easier said than done, of course, but it's a method to cryptanalyze the ciphertext, right? But you need to know the size of the key. Well, the idea is that a good candidate for the size of the key is the greatest common divisor or a divisor of these recorded distances of groups of 3 or more letters. Is not greater than 3, is actually greater or equal to 3. So for instance, this ciphertext, of course, is not going to work on small ciphertext. It's never going to work on small ciphertext, any of these methods. So if you have a ciphertext of 4 letters, then it's as good as unbreakable. So for instance, in this case, again, made up example, if you look at the BUK, you see 18 minus position. So this occurs at position 18, and this occurs at position 10. 18 minus 10 is 8. I will try a divisor. I don't have multiple distances to come up with a GCD, but I have one. I'll try the divisors of 8, which are 2, 4, and 8, assuming that I have polyalphabetic, not simple substitution. So I'll try 2, 4, and 8. Well, believe it or not, in this case is actually 4. But that's, it's just an idea, right? So I will have to try 2, 4, and 8. as you can imagine, probably, I mean, if I could go into mind of the person who encrypts the message, it makes kind of sense for the size of this alphabet given the size of the cipher or plaintext, the size of the ciphertext, to take something in the middle, not too large and not too small. So I would actually try first a 4 as opposed to 8. You see, I'm using even a bit of psychology to cryptanalyze this test. Now, the general method to deal with the polar overlay cipher is based upon Friedman index of coincidence. This was invented in 1920. He's well known in the crypto community. He had a grant apparently, so he was employed by the eccentric millionaire George Fabian. I've seen actually the lectures and the little book that he wrote on the statistical analysis of the language. You can probably find online as well. William Friedman. Very important of what he says. Some recent methods, some current methods that actually people are using are based upon some things that he hinted to, again, in the beginning of the 20th century. So here's actually what the idea is. Again, we start up a little bit more mathematics, and I'll continue with more mathematics tomorrow by looking into the block cipher design and such. Again, assuming the ciphertext is in English, I being faced with the ciphertext, and I'm counting number of A's and B's and so on and so forth. Of course, the size of the ciphertext is the sum of all these counts, n0 plus n1 plus up to 25. And now I'm defining the index of coincidence to be n0 choose 2, n1 choose 2 plus n25 choose 2 over n choose 2. Now, what does this count? What does this do? Well, this gives the probability that two randomly selected letters are the same. Let me repeat this. So it gives the probability that two randomly selected letters are the same. Of course, n0 is the number of A's in the text. So basically, obviously, since I have n0 in the text, what is the probability? Is n0 choose 2, right? Of selecting two A's in the text. And you keep on doing that. Again, the randomly selected letters are the same. For plain English, the probability of two letters are the same is obviously p0 squared plus p1 squared and so on and so forth, which is 0.065 is the probability of the ith letter. Now, somebody might ask, well, hold on a second, how do you compute this? I mentioned a while back in my talk that even if you do take the Library of Congress in the beginning of the library, or any library in the beginning of the 20th century, or the current one, the Library of Congress, you will see that perhaps this number may have changed after the seventh letter or so, seventh digit, but it has not changed much in spite of the fact that any natural language evolves. So this number here is basically the probability of this probability that I have on the screen, p0 squared. That basically is you count in a book or multiple books the number of two letters being the same, right? In that book or multiple books, A's and B's and so on and so forth, you will come up with 0.065. Of course, randomness is different. It's 1 over 26. Of course, the index of coincidence is 1 over 26. Surely, you will see that because in a random approach, any two letters are equally likely, right? So A is as equally likely as C or W or something like this. If it's random, if it's purely random. Of course, I have 1 over 26 squared 26 times. That means it's 1 over 26 squared plus 1 over 26 squared 26 times, which means it's 1 over 26. So ultimately, randomness in any natural language is 1 over the size of the alphabet. So please remember that, because I'm going to display some things later on. Now, how do you estimate this index of coincidence to come up with the length of the keyword in visionary cipher? Remember, I mentioned to you that what you do is you basically, the size of the key is the number of alphabets that you're using to encrypt the various letters in your plaintext, right? So let's say K is the size of the key, the message is of length n, and now what I do is I'm going to chop off my ciphertext into K columns, and n over k rows. Well, surely, n may not be divisible by k, so it doesn't really matter for us. In crypto, what we do is pad. So there are methods of padding, or we just keep it on, unpadded. For this particular purpose, we keep it unpadded, of course. But in reality, for whatever purpose, we usually pad it just to suit our purpose, okay? Sometimes we actually pad it on purpose, right? Now on each column, that's the idea. On each column, I'm using the same alphabet now because, again, let's say MITH, like I had before, M was the first alphabet, is the shift for the first alphabet, A was the shift for the second alphabet, and keep on doing that. That means that if I chop off my ciphertext into k columns and n over k rows, in each column I have the same alphabet. Aha, that's interesting. So now selecting two letters from the same column is like selecting from simple substitution because I'm using the same alphabet. Now two different columns is like selecting random letters. Because I'm using different alphabets, there is no correlation between the two alphabets, which means that it's like selecting random letters. That's important, actually. And this was the brilliance of the methods of Friedman's method. Now, let's compute the index of coincidence, for instance, for now the expected, obviously, remember that the 0.065 was the natural language index of coincidence. So selecting from the same column, but two different rows is like selecting basically from different alphabets of the same letter, right? So this is the expected value, right? That's the natural language. N over k choose 2, because that's the number of rows there, times k, which is the number of columns. So this is the number, basically the index of coincidence, or the instance of that for, again, selecting the same column but two different rows. Now, if you select from different columns and any two rows, of course you get k over 2, which is, and n over k, which is the number of rows in there. So choose the two columns, any two rows. I have n over k rows, choose one, choose the second, it could be the same row. And now I have k over 2, which is the number of columns, or k is the number of columns, k choose 2 is the number of choices I make for those columns. So this is the expected value for the randomness. Again, this is the probability that, we get random. It's 1 over 26, right? Okay, perfect. So now let's add them up. This is, what happens in my ciphertext, right? This is always what happens in my ciphertext, depending upon the ciphertext, right? So this I should be matching this particular expected value given k, I don't know what k is, but a putative k for the size of the key. So this, again, depend upon the ciphertext, should match this one, which is, computed given some putative size for the key. I'm solving this equation, simple equation, and I come up with k approximately this number right here. As I mentioned to you, in practice, we simply use this approximation. I'm not going through this process before, but you should probably see this once in your lifetime just to assess where that guess is coming from. It's an educated guess for the size of the key. So k is approximately 0.0265 for n and blah, blah. Again, I is the computed index of coincidence from given the ciphertext. You have it in front of you, you compute that, right? So again, using n, which is the size of the ciphertext, using I, which is computed index of coincidence, I come up with a guess for the key. In reality, again, just because it's an approximation, perhaps I should have gone with more digits in there. I'm using basically for the size of the key, I'm using neighbors of this k. For instance, if k would be 4, I would use 3, 4, 5, possibly even 6 guesses for the size of the key in the polyalphabetic cipher. Now, for given, I'm teaching a crypto course at my place, and I've been doing that for the past, many years, perhaps 12 years or so. And depending upon the people in my class and what languages they're speaking, I usually investigate the index of coincidence for other languages. And I have here, let me see if I can display a little smaller so you can see it. These are the normalized index of coincidence for other languages. Arabic, again, this is the natural language. So Arabic 0.07, 28 letters. I probably should have displayed to you 1 over 28 just to give you a glimpse into, so 1 over 28, is 0.03, something like this. English 0.06566, 26 letters. Finnish and French and German and Greek and Hebrew. Hindi, for instance, is 0.14 if you use 47 letters. Italian 0.07. Again, 1 over 47 is actually is 0.05, right? 0.005. Well, what's interesting about this is there is a huge distinction between random in Hindi and natural language. So you guys, I mean, whoever speaks Hindi has a very clear rule on how the sentences and the words are actually formed. So natural language actually is quite well determined. Japanese, I'm using hiragana and katakana, 83 and 86 characters, again, large, 0.06, 0.07, even Romanian, my mother's tongue, Russian and Spanish and Swedish. I want to point out the fact that most of these actually have between 20 and whatever number of letters, but there is a jump of at least a factor of 2 between random and natural language. So we can quite easily distinguish whether in whatever language one uses a simple substitution or a polyalphabetic cipher, and I can detect what was going on there, and I can actually try one method or the other. So this is one thing that I like to point out. Here's an example. Let's say I'm receiving this, or I'm intercepting this ciphertext, and I want to cryptanalyze it, and I kind of guess, well, there is a reason for that, that I'm using a polyalphabetic cipher. So A occurs 24 times, B occurs 13 times, and keep on doing that. Now, I'm counting the 438 letters, that's the size of my ciphertext, and I'm computing the index of coincidence. Exactly as I mentioned to you, ni minus 1, sum up of that over ni minus 1, which is n I choose 2, the sum of those over n choose 2, that's the index of coincidence given the ciphertext, right? And given these counts, I'm computing it and I come up with 0.4116. So this is closer to 0.0385 than 0.065 or 66, as I mentioned earlier, which means that my guess is that the designer or the person who sent the message used the polyalphabetic cipher and not a simple, because it's closer to randomness as opposed to, natural language. It's closer to randomness, which is 0.03, as opposed to 0.06, which is the natural language. So I'm using the formula that I displayed before. I'm computing that, and I come up with, hopefully I didn't make a mistake here, 9.63539. So K is approximate 9.6. Well, what do I use? 8, 9, 10, and possible other values. In fact, the key length happens to be exactly K is equal to 8. And again, if time would permit, I would actually go through the entire process. Now, block ciphers, I will go through it tomorrow, but I just want to point out again, because this is a historical session, I want to point out that we encounter in every standard that we have nowadays, we encounter some instance, some idea of what a cipher that was invented again in the beginning of the 20th century by Hill. And in fact, by mistake, this cipher was actually used in one of the Sony's first encryption key on one of the initial disks. It was obviously cryptanalyzed, and I remember actually Misha Mihalchevich, one of my friends, cryptanalyzed this cipher 20-something years ago, I guess, that Sony has used. He broke it. So here's the idea behind it. I like it because, you see, up to this point, every letter was encrypted by a single letter. So Shannon's principle of diffusion actually was not achieved much. So Lester Hill, actually, 1929, he even built a machine to actually use the cipher. So ultimately, what he did was he took basically a key that was a matrix, n by n key, let's say in English, Z sub 26. Every entry in that matrix was a residue modulo 26. Assuming that you have a plain text of a certain size, you chop it off into pieces, and then you take a block of size n, and you basically multiply by a secret key m, from the left or right, doesn't really matter how you do it, as long as you know, the recipient knows exactly what you use, right? So let's say CI, the ciphertext, which is again a block, is MPI modulo 26, or from the left, PIM modulo 26 for row plaintext. Again, the encryption is rather very simple, either M inverse CI or CIM inverse. I mentioned to you this is still a symmetric cipher because knowledge about M, if you know the matrix, the encryption matrix, you also know the encryption matrix by simply finding its inverse. We have lots of methods, from Gauss 1777, 1855, methods that can give you the inverse, within a certain amount of time. I like it for many reasons. Here's an example, for instance, let's say n is equal to 3. I'm taking this one. Of course, the matrix has to be invertible. Otherwise, you cannot decrypt it, right? And you multiply this, let's say ABC 0, 1, 2, by the matrix from the left, you get the AXW, which is a ciphertext. Surely, to decrypt it, you compute the inverse, and then you multiply from the other side by the inverse. You multiply the ciphertext by the inverse. Now, I like it, as I mentioned, for a variety of reasons, because it satisfies, the Shannon's principles. A single change, let's say my plaintext would be BBC instead of ABC. If I multiply BBC by the same matrix, I get BZZ as opposed to AXW. So a lot of changes in my ciphertext is just a simple change in my plaintext, because you diffuse. You see, a single letter may have effect in multiple letters in your ciphertext. That's actually one idea that I liked about the sealed cipher. Of course, is if you intercept enough characters, you can easily cryptanalyze it. It's not that difficult to do. But the idea occurs in many ciphers, many current ciphers now. Okay, so I don't want to go to the one-time pad. Everybody knows that. But I want to go to the summary of what I mentioned to you. Linear ciphers are weak, as I mentioned earlier. Strong ciphers must have high nonlinearity. I will show you that every cipher employs linearity because they're fast in practice, but they have to have a high nonlinear component in there that actually reveals or renders the security of that particular cipher, whatever the nonlinearity flavor is. Now, exhaustive key search is obviously is fair, divide and conquer. Statistical analysis, exploit linearity, any combination of this, all fair in love and war, and obviously cryptanalysis. And I wanted to finish up before the clock, and I have done so. Thank you very much for your attention, and hopefully I'll see some of you in the block cipher, which is a bit more mathematical and a bit more hands-on, involving even the current ciphers tomorrow. Thank you. I welcome questions, surely.
Thank you, Pante, for the wonderful talk. So are there questions from the audience? You can unmute yourself or you can write your questions in the chat box. So if there are any questions, somebody has written in the chat box, it seems. Oh, what time is your lecture tomorrow? It's at the same time. Yeah, okay.
It's the same time, yes.
Yeah. So there does not appear to be any question as such. So
it's probably cipher. So
yeah.
One question written in chat box: using coding theory, can anyone break in codes?
Okay, yeah. There is one question in the chat box. There is one more question.
What are you referring to? Using coding theory, you mean the encoding, not the encryption? Because we distinguish between encoding and encrypting. So encoding means.
There is another subsequent question by the same person. Is there any relation between cryptography and coding theory?
They all go hand in hand. You see all the time. So let's say you have a communication channel, right? So the sender, Alice, she will basically have to encode the message. Sometimes is done beforehand and then encrypted. Sometimes he's actually encrypted and then encoded and sent through the communication channel. Of course, the communication channel will have noises depending upon the, whatever the communication channel, which means that you have to encode it. So of course they go hand in hand. We always, if somebody is expert in cryptography, they have to know a little bit of coding theory as well, or a little bit or a lot more coding theory, and vice versa. So there's always obviously connection between cryptography and coding theory. Of course, the recipient end, the recipient will have to assume that noise has been inserted in the channel, which means that they will have to use coding theory methods first to decode, probabilistically the ciphertext, and then use the crypto methods to actually decrypt. So we use encode decode for coding theory version, portion, and encrypt decrypt for crypto portion of the communication. Okay. Thank you for
Yeah, there are a few more questions. So can we think of noises as an encode, or can we think of coding theory to hack those codes? Of course, the question is not clear to me, but I just read it out for you. Yeah.
Can we think of noises as an encoding?
Yeah.
I don't know exactly what you're referring to, but
the question.
Maybe he's referring to some of the current methods, actually, some of the post-quantum algorithms to basically insert noises. Sometimes we actually insert noises just to counter the side channel attacks. So there's a lot more than the bird's eye view that I gave here. We literally insert noises into the ciphertext just to counter side channel attacks, because sometimes it's easier to, you see, in bitwise, 1 + 1 has the same answer as 0 + 0, but one of them is more expensive to compute. So of course, if you measure, for instance, the heat and all that in an encryption method, if you have a large enough ciphertext, you can probably guess whether the outcome 0 came from 0 + 0 or 1 + 1. Again, I'm simplifying this to death, just to give you an idea. Well, just to be able to counter that, yes, we insert noises. We basically compute things that has no relevance to the plaintext or the ciphertext, just to fool a side channel attack. So of course, those noises have to be taken out at the recipient. And of course, we use various methods. Maybe this is what the person was referring to.
Maybe. There is another question by Manish Patel. How do we protect the encryption key? Because the further encryption will change the problem rather than solve it.
How do we protect the encryption key?
Yeah, that's the question.
Well, first off, as I mentioned to you, we have two methods, symmetric and asymmetric. And if you use, for instance, a key in a symmetric cipher, you exchange the key via an asymmetric method. So for instance, somebody wants to send me a message, they will take my public key that I designed, only I will know it, and they will actually use it in a symmetric cipher, for instance, or asymmetric, depending upon whatever they prefer. So this is basically how you protect it, by simply not telling it to anybody and making sure that whatever design you use to come up with that particular encryption key respected the rules. In other words, the rules means they are, even in the strongest ciphers out there, they are weak keys. For instance, I sometimes, use various known methods of breaking, for instance, even RSA in real time. I literally tell my students to choose some keys and then choose some prime numbers and multiply them and give me the product, and I will find the factorization in real time, just because I fool them by telling them to take prime numbers, for instance, they have a certain size, there is actually, smaller or encryption exponents that are smaller than a certain size of the key. I say, well, I can probably do it more, if I spend more time, but choose one that is smaller than 100 digits or something like this. But because I know something. So in other words, respecting the rules should actually make sure that the key is sufficiently stronger for symmetric or asymmetric communication.
So there is another question by Ridima Takral. Is there any better method than masking as a countermeasure to side channel attacks?
A better method than masking?
Yeah.
Personally, I don't think so. I mean, there are some proposals out there, but masking is of different flavors as well. So there are various flavors of masking. For instance, I work in, side of my research is done on crypto Boolean functions. And for instance, one masking that people are using is by using the low correlation immune functions. This has been brought out not too long ago, and it seems to be quite well received, but this is not the only method. So personally, I like it. I haven't investigated just because this seems to be quite good. That's what I'm saying. So I haven't investigated the other proposals much, but there are some. Yes.
There is another question by Aditi Kulkarni. Can you suggest some book that one can refer to know more about the history of cryptography?
Oh, yes, surely. So I personally have myself quite a few books. Believe it or not, it's the first one that is not specifically for decryption or coding or cryptography, but the first book where I encountered the crypto system was when I was in 6th grade, and I read Jules Verne. Believe it or not. So it struck me that somebody was about to be hanged, and there was his innocence actually was hidden in a cipher, and they ultimately decrypted that message by guessing that the person who sent it also signed it by encrypting the message, and they knew something about the signature, and that's how they encrypted it. But that's not really about history. But this is the first book that I encountered as a child where encryption was used, and it struck me, and I sort of got attracted to that. Codes, obviously, is one nice book on history of cryptography. Several more that don't come to me right now, but I can surely, I can have a list tomorrow morning if somebody is interested, if I don't forget.
There are a few comments, not the questions. There is a comment by M.S. Chang. Perhaps we can say that coding is to add protection to the message towards error caused by the noises, whereas crypto is to add protection to the secrecy of the message.
Absolutely.
Yeah, absolutely. Another comment I find interesting, the part computing IC and calculate the keys for each language. Can I ask, where can I read these statistical properties about it further?
So I was invited a while back by Bimal Da, to give probably some of the people in the audience, actually, I know for sure they were there, to be one of the National Cryptologic Days speaker. And I traveled there maybe 4 years ago or 5 years ago, I forget when it was. I've been going to India every year since then, except for obviously this year and last year. There is a point to my story. And during my talk, I also mentioned a little bit about some of the languages, and some of my friends are Bengali and in other areas of India. And I was displaying the index of coincidence for some of these languages. And I said, well, you know what? I find it interesting that you guys have, 80 something or 19 languages probably that are official. And I don't find the index of coincidence for all of them. Perhaps it would be a nice and interesting project for some of the undergraduate students or even some of the master's students actually to to digitize and take some of the books in whatever language and try to see and publish, for instance, the index sequences for that particular language. It could be interesting. Again, it's a nice problem. So I found actually a few years after my push for that, I found a paper on the index sequences of a language of an official language in India. I like to think that it was my suggestion, although probably wasn't, but who knows, doesn't matter. Now, about the other languages, there are actually books on statistical properties of the index sequences and such. I will suggest for you to download, for instance, Friedman's report. It is a nice and interesting, a lot more than I have presented here, but it gives you a glimpse into the statistical analysis of natural language. And again, I find it interesting, regardless of what the language is, there is a jump of a factor of at least 2 between random and natural language. So it doesn't matter whether the language seems random to you, how they concatenate, 5 consonants in there. There is a rule. There are rules for making up that particular word. I speak a few languages, and I know for sure that there are rules for whatever language. Thank you so much for all the other comments. And so if somebody is interested in you guys are posting the talks on YouTube or whatever, right?
Yeah, Pante, I mean, if you can share your slides with us, we can make them.
Oh, sure. I'll send to you and Sartaj actually the slide, surely. Of course.
And then the videos, we will share with you the recordings, and then if you allow us, we can.
Yeah, absolutely.
Yeah.
Absolutely. Thank you so much for attending.
Thank you so much for your wonderful talk once again, and looking forward to your next talk tomorrow. Thank you so much.
Absolutely. Yeah.
Okay.
Thank you, guys.
Okay, thank you. Let's thank all the speakers in this session, and see you tomorrow.
Thank you, sir. Thank you very much.
Thank you, Dr. Sartaj. Dr. Sartaj, thank you very much.
Yeah, thank you. Thank you so much to you as well, actually. Yeah.
Yeah.
Okay, so good night, at least for India.
Yeah.
Good night, sir. Good night.
Hello, Bhatendu sir. कैसे हैं आप? I cannot hear you. You have to unmute yourself.
Thanks a lot to all the organizers, Dr. Gorpade and Dr. Sartaj. Yes, of course.
Thank you.
Nice, wonderful talks are going on. All the talks were really nice.
Thank you, sir. Thank you.
Thank you. Bye.
Okay, sir. Bye, sir. Good night.
Okay, good night.